Good morning to Ananda. Good morning. So you please kindly confirm audio, video, and screen once. Please kindly confirm audio, video, and screen. Yeah, thank you. Thank you. Yeah. So let's see some problems in this chapter. So you go with this first one. So it was a previous gate examination question. Previous gate examination question. Very simple thing only. Very simple thing. Just look at it. See, sir. See the reflection coefficient of the transmission line shown in the figure. Reflection coefficient of the transmission line shown in the figure at the point P. At the point P is very simple thing. See, we have a transmission line with a surge impedance of 300 ohms. We have a load resistor. Load resistor also of 300 ohms. Both are exactly equal. Then whether the wave is going to experience any reflection or not? No. So we don't have any reflection at the point P. Which reflection you don't have? Is it voltage reflection or current reflection? Both. I don't have either voltage reflection or current reflection. So both reflection coefficients will be 0. Both reflection coefficients will be 0. Okay. So I can write here in the solution, simple, as load impedance is equal to surge impedance of line, which is nothing but 300 ohms. So no reflections experienced by the wave. So I can say V reflection is equals to 0. I reflection also equals to 0 at the point P. At the point P, we don't have any reflection. We don't have any reflection. Okay, so answer is C. Answer is C for this one. C. Simple question. Okay, so let's take the next one. Next one. So I'll show here. So it is also a previous gate question asked in 2010 gate examination. 2010 gate examination. Go through it. Consider a step voltage wave of magnitude 1 per unit. Consider a step voltage wave of magnitude 1 per unit traveling along a lossless line. Terminates in a reactor. See, we have a lossless transmission line here. This is a lossless line. Terminating at this point A. Terminating at this point A with a reactor. It was a reactor. Okay. The voltage magnitude across the reactor. Voltage magnitude across the reactor. At the instant the traveling wave reaches the reactor is. Right? We have a 1 per unit wave traveling on the transmission line. At the end of the line, we are finding one reactor. And what will be the magnitude of volt across the reactor at the instant when this traveling wave reaches to that location? Okay. See, first of all, this reactor, what we have, listen please, all of you. The reactor, what we have here, how is the behavior of reactor with respect to sudden transient? Is it going to act as an open circuit or short circuit? Is it going to act as open circuit or short circuit? Reactor. It will be acting as open circuit because it will be opposing the sudden changes in the current. Okay. See, as it is acting as open circuit, can I say that? Surge impedance of the reactor is equals to infinite. Surge impedance of the reactor is equals to infinite. Yes or no? Yeah. So I'll say in the next slide. Just observe here in the solution. reactor acts as open circuit during sudden transients. During sudden transients. Reactor acts as open circuit during sudden transients. Okay. So not only that, I can say surge impedance of this reactor will be equals to infinite, I can say. ZS I am calling here. Surge impedance of the reactor is equal to infinite. Yeah, please tell me. Whenever this is infinite, so obviously it is acting as open circuit, we are saying. So when the surge voltage is propagating towards the end of the line, and if it is looking at an open circuit, what will happen to resultant voltage? Or what will happen to the refracted voltage? Tell me please. What will happen to refracted voltage or resultant voltage now? That will be definitely equals to double. That will be definitely equals to double. Or you can say it is 2 per unit. 2 per unit. So I can say here, that implies voltage across the reactor, at the time t equals to capital T. I will show the diagram if you want. I will draw the same diagram in the solution also. In the solution also, I am showing the same diagram like this. Okay. So this is at the time t equals to 0 plus, and the wave is propagating, reaches to this junction V, and this is a time t equals to capital T, and refraction will be V2 and reflection will be V1 you have, and the refracted voltage V2 will be equals to double the value of incident. Double the value of incident because of the open circuit behavior. So it will come to be 2 per unit because the voltage V is set as 1 per unit. Voltage is set as 1 per unit. So obviously it will become double, 2 per unit. Okay, next thing. See, this type of element, what we have, reactor, shunt reactor bank, I will call it as lumped inductive element. Lumped inductive element. Lumped means physically it is small. Physical length is small. Lumped. Inductive means we have a coil. That's the meaning. Lumped inductive apparatus. So-called shunt reactor bank, will have a surge impedance equals to infinite in the ideal condition. Any other apparatus we have? Any other apparatus having the surge impedance equals to infinite? Any other lumped inductive apparatus we can consider? Any other lumped inductive apparatus we can consider? Transformer. Transformer is also one of the best example. So transformer is also going to act as open circuit during the surge propagation. Okay. Yeah. So I can say here, for lumped inductive apparatus, inductive apparatus, in bracket, for example, shunt reactor, one thing. Shunt reactor. Next one we are saying it is a transformer. Transformer. For these things, surge impedance is equals to infinite in the ideal situations. Ideally speaking, it will be infinite. Practically speaking, this number will be in the order of thousands of ohms. Practically, it will be in the order of thousands of ohms. Okay. So I can write ZS equals to thousands of ohms. Practically speaking, it will be in the order of thousands of ohms. That's the meaning. Yeah. Similarly, let me ask you another question. Lumped capacitive apparatus. The best example is the shunt capacitor bank. So you know already capacitor won't accept sudden changes in the voltage. So it may act as a short circuit for a sudden transient. So if it is acting as short circuit for sudden transient, surge impedance will be equals to 0 for the shunt capacitor bank, ideally speaking, but practically speaking, it's a very low number, maybe in the order of tens of ohms. Okay, so I can write here for lumped capacitive loads or apparatus. for lumped capacitive apparatus. The best example what we are saying is a shunt capacitor bank. Shunt capacitor bank. So for this, surge impedance will be equals to 0. Ideally speaking, it is 0. And this number will be in the order of tens of ohms, practically speaking. Tens of ohms, practically speaking. Very, very low. Practically speaking, that number will be very, very low, we can say. Very, very low. Yeah, done. See, till now, in the first two problems, what we are saying. First one, we have taken a distributed model, terminated with a lumped resistor, terminated with a lumped resistor. Next problem we have seen distributed model terminated with a lumped reactor, right? And further, what we are going to discuss is distributed model terminated with one more distributed model. Distributed model terminated with another distributed model. That type of problems we are going to discuss further, right? Look here, for example, you see this is a first distributed model having a surge impedance of Z1. First distributed model having a surge impedance of Z1. And second distributed model connected in this manner with a surge impedance of Z2. Z1, Z2 are surge impedances, not the series impedance. Not the series impedance of line. These are surge impedances. Okay. Next, this is the junction or the discontinuity point, you can say junction. Just observe. See, we are switching a voltage V onto this line. Initially, let me talk. We are switching a voltage of V onto this line. How much current is getting created in the propagation? Voltage V you have injected. How much current is getting created in the propagation? Anybody please tell me. How much current is getting created? V by Z1. That's it. V by Z1. We no need to bother about Z2. We no need to bother about the Z2. Why? Why in the sense we are injecting voltage on the line of surge impedance Z1. According to Z1 surge impedance, current is getting created. And this voltage and currents will be propagated on this line and reaches to junction. Then the wave is going to face the impedance of Z2. Then only it will face the impedance of Z2. Okay. See, let's say V comma I was injected here. Let's say V, you talk about only voltage V injected. So Z1, Z2 are unequal. Z1, Z2 are unequal. So that we have a refraction V2 which may not be equals to V. We have a refraction V2 which may not be equals to V. So that I have to add a V1 mathematically to V to get that resultant voltage on the first line also as a V2. This is a general procedure what we have to think. How to calculate the value of V2 now? How to calculate the value of V2? Anybody? How to calculate the value of V2? See, actually, in the equations what we have discussed, we have taken a distributed model terminated with a resistor and we have done all things. Okay. But here, listen please. We will assume that this Z2, of course, it is a resistive in nature, already we know. Z2 is already resistive in nature, that we know already. And this Z2 what we have, that I will be assuming as a resistor. Assume that it was a resistor here. It was a resistor connected. By assuming that as a resistor, your V2 value will come to be 2V into Z2 by Z2 plus Z1. 2V into Z2 by Z2 plus Z1. Like that, we are going to get this. Okay. And that V2 will not stop here actually. That V2 will propagate on the second line. V2 will propagate on the second line. Reaches to the end of the second line. And again, it may face some more discontinuity and it will be continued. So I think all of you getting it. Okay, so the formula what we have discussed earlier, we are going to use for the calculations of the reflections and refractions in these cases also. That's the intention of this discussion. Okay, let's take up some more problems quickly. So I'm taking up the next problem here. Go through it. Say so. So an overhead line having a surge impedance of 400 ohms connected in series with an underground cable. We have an overhead line with a surge impedance of 400 ohms connected in series with an underground cable of surge impedance 100 ohms. Okay, done. If a surge of 50 kV travels from the line towards the cable junctions. 50 kV travels from the line towards the cable junctions. Okay. The value of transmitted voltage wave at the junction is how much? The value of transmitted voltage wave at the junction is how much? Simple. See, the value of the transmitted voltage wave or the refracted voltage, junction voltage, voltage experienced by the cable, all these things will be same. All these things will be same. Let's look at the question first. We have a overhead line with a surge impedance of 400 ohms, we said. So like this, we have a overhead line of surge impedance 400 ohms. ZL. Next thing, connected in series with a cable. So this is a cable surge impedance. I'll call it jet cable. Jet cable surge impedance of the cable is 100 ohms. He said 100 ohms. Okay, next thing, 50 kV surge is traveling from the line towards the cable junctions. This is a surge of 50 kV. Surge of 50 kV traveling from the line towards the cable junction. This is a junction of line and the cable. Junction of line and cable. Okay, next thing. Look here, please. That V 50 kV propagating on the line, reaching to the junction. V incident I will call. So we have a difference in the surge impedances. Because of that, the refracted voltage will not be same as the incident voltage. So we get a reflection of V1. I can say. Okay, please tell me. What is that V2 formula? V2 is equal to 2V into, very simple thing. Don't confuse and don't look back to the formula what we have discussed, please. Don't look back to the formula what we have discussed. Just take the incident voltage double 2V into impedance after the junction, jet cable by jet cable plus jet line. Jet cable by jet cable plus jet line. That's it. Voltage division principle you have to apply. Jet cable plus jet line. So it is 2 into, what is the incident voltage we have? 50 multiplied with cable surge impedance is 100 by, it is 100 plus 400. So it will be 100 by 500. So it's 1 by 5. It will come to be 20 kV, I think so. 20 kV. That is a refracted voltage. So it's only surges. We are discussing about only surges. Yeah. So I'm saying again, very simple thing. We have a overhead line connected in series with a cable. 50 kV surge is injected on the overhead line. That 50 kV was traveling towards the junction, facing a surge impedance of 100. We have a mismatch. Because of that, resultant voltage will change to a value of V2. So that we have a reflection of V1. And what is the equation for V2? Take the voltage times 2V into impedance above the junction, jet cable by jet cable plus jet line. Just like voltage division, by taking voltage as 2 times. So if you keep these numbers, you will get this value as 20 kilovolts. 20 kilovolts. Yeah. So let's look at the next question. All these questions, whatever I am discussing, are from our workbook only. From our classroom practice questions. Already have uploaded this file and I have advised you many times to take a print out of it. Okay. Yeah. Please go through this question. Almost similar one, but here we have first cable, next we have line. In the previous problem, first we have a line, then cable. Now it is first cable. The next element is a line. Okay, go through it, please. Go through this one. So what is the voltage experienced by the line if 110 kV surge voltage reaches to junction of the cable and the line? Look here, please. We have a cable and we have an overhead line. Right? 110 kV surge voltage has to reach to the junction of the cable and the line. Okay. And cable, he said L and C some numbers. And whereas for line, he said some L and C, millihenry by kilometer. Okay. And you have to choose one among these options for the voltage experienced by the line. That is nothing but refracted voltage, or you can say transmitted voltage, or you can say junction voltage. All these things are same as we have discussed many times. Okay. Let's say here, let's say the solution. This is a cable we have, cable. And in series with that cable, we have a line. In series with that cable, we have a line. Okay. So cable L and C, L for cable, 0.185 millihenry by kilometer. 0.185 millihenry by kilometer. C, it is 0.285 microfarad by kilometers. Microfarad by kilometers. And line L, it is 1.24 millihenry by kilometers. And capacitance of this line is 0.087 microfarad by kilometers. 0.087 microfarad by kilometers. Yeah, so they don't give time, just they will ask you for the first time. They don't give time, they will ask you only for the first time. First time when the wave reaches to the point, how much is the refraction? That's what he is asking, no? Simple. Why you are bothering about time now? Okay. So injected surge voltage, he said 110 kV, reaching to the junction of the cable and line, right? At some amount of time, whatever it is. Incident is V. Definitely we are going to get some mismatch. Who is going to decide that mismatch? Surge impedance of cable and surge impedance of line will decide it. Okay, let's calculate first. Let's calculate. What is surge impedance of line? Sorry, cable. Root of L by C is a formula for anything. Surge impedance of cable, root of L by C. So root of L by C means 0.185 milli by 0.285 micro. Root 0.185 milli by 0.285 micro. And similarly, you calculate the surge impedance of overhead line. Surge impedance of overhead line. So it will come to be root of L by C means 1.24 milli in the numerator by 0.087 micro in the denominator. Yeah, please tell me, what is surge impedance of cable? Cable and overhead line. Tell me these numbers, please. 25.7 and 25.5, 119.38. 25.5 ohms is the first one. Next one is 119.38 ohms. Okay, so we have a change. We have a mismatch. Because of that, definitely the refracted voltage will not be same as incident, and we get a reflection of V. We get a reflection of V1. Okay, what is V2? What is V2 formula? Anybody please tell me. V2 formula. 2V into Z line by Z line plus Z cable. Voltage division. Voltage division. Take the voltage 2 times. So it is 2V into Z line by Z line plus Z cable. That will give the value of V2, which is nothing but the refracted voltage, or you can say voltage experienced by the transmission line. So it is 2V into line surge impedance by line surge impedance plus cable surge impedance. So it will be 2 into V is 110 kilo, and Z line is a number 119.38. 119.38 by 119.38 plus cable surge impedance. It is 25.5. It's in kV. It's in kV. How much is that? Anybody? 181.3. It's the best way of remembering Thevenin model. Best way. Just it's 2V and line impedance and load. That's it. What is the best way of remembering it again, Vishnu? Very simple network only, no? What's the way of remembering again? 181.3 kilovolts is a V2. Thevenin model you have to remember. That's the easiest way. Easiest way. 181.3 kV. That is a refracted voltage V2. Refracted voltage V2. Okay, let's have a comparison between these two problems. First problem you see once. Surge is propagating from overhead line to cable. Look all of you, please. Look all of you. I will ask one very simple question. Just listen. Surge voltage is propagating from overhead line to cable. Means high surge impedance to low surge impedance. High surge impedance to low surge impedance. What is refracted voltage? 20 kV. Okay. What is incident? 50. Look all of you, please. Look all of you. 50 kV incident. Right? See, listen. Assume that at time t equals to 0, this 50 kV injected on the line. 50 kV injected on the line, and 50 kV is getting developed at all the places on the line. Reaches to the junction at a time t. Capital T. Then what is the refracted voltage you are getting? 20 kV. What is happening to that voltage? I can say, is it decreasing? Is it decreasing or not? Yeah. Is it decreasing or not? Yes, definitely. Definitely it is decreasing. So what you can say is, if the surge is propagating from overhead line to cable, it is expected that surge voltage magnitude will be decreased. Okay. Next, if it is propagating from cable to overhead line, injected surge 110 kV, refracted surge 181.3 kV. So surge voltage magnitude will be increased, we can see. Okay. So anyhow, so I'll write here in two statements. First statement is, the surge propagates from overhead line to cable. Means from high surge impedance to low surge impedance. Overhead line to cable. Then surge voltage magnitude reduces. Surge voltage magnitude reduces. Okay. Whereas in the other case, if the surge is propagating from cable to overhead line, surge voltage magnitude will increase. Leave some 2 to 3 lines here. We are going to write some more things there. Leave some 2 to 3 lines and you write here, the surge propagates from cable to overhead line. Surge voltage magnitude will increase. We can write surge voltage magnitude increases. Surge voltage magnitude will be increased. Surge current, it is in opposite way. For example, if you look at the first one, in the first case, surge current will increase. And second one, surge current will decrease. In this case, surge current magnitude increases, and here you can say surge current magnitude will decrease. First case, surge current will be in opposite way. Current will increase in the first case, current will decrease in the second case. How? In the sense, just you calculate those refracted currents, compare with the incident current, you will come to. Okay? Yeah. Next thing. One more simple thing I want to tell you. I don't want to complicate this to you. I'll try to tell in a simple way. Right? Some people might be clear about it. Just look here once. We injected a 50 kV surge on the overhead line. Injected a surge of 50 kV on the overhead line. That is propagating on the overhead line. With some rate of rise. As time progresses, there is a development of voltage on the line, right? As time progresses, there is a development of voltage on the line, so that we expect that surge, 50 kV surge is rising at some rate. There is a rate of rise for the 50 kV surge voltage. That's the thing I am saying. There is a rate of rise for the surge voltage what we are seeing. But after reaching to the junction, surge voltage was decreased to 20. Surge voltage was decreased to 20 kV. Can I say now? Rate of rise in the surge voltage decreased? Can I say now? Rate of rise in the surge voltage decreased. Yes or no? Yes or no? Because surge voltage is decreased, na? Surge voltage value was decreased. So we can say as a overlook, we can say the rate of rise in the surge voltage is also going to be reduced. That rate of rise is going to be called generally steepness, gradient, like that we are going to name it. Okay, so I can call here steepness in the surge voltage will decrease. In this case, steepness in surge voltage, decreases. Whereas in the other case, surge voltage magnitude is rising up. So we can expect that steepness in the surge voltage is going to be increased. We can expect that steepness in the surge voltage will be increased. Whereas steepness in the surge current, it's in opposite. Steepness in the surge current in the first case increases, second case decreasing, we can say. So here you can call steepness in surge current increases. Steepness in the surge current increases. And here you can say steepness in the surge current. Steepness in the surge current reduces. Steepness in the surge current will be reduced. Steepness is nothing but rate of rise. Steepness is nothing but rate of rise. Okay. So these are some conclusions what we have to know regarding the surge propagation from one to the other, from low to high or high to low. Okay, let's look at the next problem. Next problem is related to this only. Yeah, see this. So previous civil services examination question. Go through it once. Yeah, check this please. See, a short length of cable is connected between dead end tower and substation. Short length of cable is connected between dead end tower and substation at the end of the transmission line. Okay. Which of the following will decrease? When voltage wave entering from overhead line to cable? When voltage wave entering from overhead line to cable. Number 1, velocity of propagation of voltage wave. Number 2, steepness of the voltage wave. Number 3, magnitude of the voltage wave. Select the correct answer using the codes given below. Select the correct answer using the codes given below. Okay, first of all, if you look at the problem, a short length of cable connected between dead end tower and substation. What do you mean by dead end tower? That's the last tower. Before the line enters into substation. This was a last tower, we can say. This was a last tower. Okay, let's look here. This is that dead end tower, or you can say it's a last tower here. Right? Dead end tower. Last tower. And we have a substation, simply like this I am showing, we have a substation. substation. See, actually, before reading that first line or before reading this question itself, first we should know that there is one overhead line. There is one overhead line running from dead end tower entering into substation. There is one overhead line running on this dead end tower entering into the substation. Like this we have. Like that we have. Okay, next. You have to read this line. A short length of cable is connected between dead end tower and substation. Between the dead end tower and substation at the end of the transmission line. At the end of the transmission line means before this overhead line entering into substation. Before that overhead line entering into substation, we are going to connect one cable. We are connecting one cable here. That's the meaning here. Okay. Before the overhead line entering into substation, we have connected one cable. We have connected one cable. Now you see, which of the following things will decrease if the voltage wave is entering from overhead line cable? Actually, you don't need to have a great idea about this diagram and all, because he said directly if the surge is propagating from overhead line to cable, overhead line to cable. So this is a surge propagating now. Propagating. Please tell me what will happen to velocity of the wave? What will happen to velocity of the wave? Tell me please, what will happen to velocity of the wave? Definitely decreases, because you know velocity of the wave propagation in the cable is less compared to velocity of the wave propagation in the overhead line. We have discussed long back. So velocity of wave propagation in the cable is less compared to velocity of wave propagation in the overhead line. So first one is okay. First one is okay, correct. Second one, what will happen to steepness of the voltage wave? Decreases. Just now we discussed about it. Steepness in the surge voltage will decrease if it is propagating from overhead line to cable. Next one, magnitude of the voltage wave, that is also decreasing. All 1, 2, 3 are correct. So answer for this is D. All 1, 2, 3. All these 3 are correct. Okay. Yeah. Next thing. Why we have to connect this cable? That's the question. Why we have to connect this cable? What will happen if you don't connect this cable? What will happen if you don't connect this cable? So let's take two diagrams here. One without cable and the second one is with cable. Okay. Yeah. So let's take in the next slide. Next slide. Case one. So I'll show without cable here. So it was a dead end tower. What we are talking? Dead end tower. And it's a overhead line. And it's a substation. And it was a overhead line. What we said? Overhead line. Okay. Please listen here. No cable is connected. Let me copy this for the next case also. Look, we are injecting a surge of V, let's say 100 kV. 100 kV surge we are injecting. 100 kV surge we are injecting. 100 kV surge. Overhead line is having a surge impedance. Let's say 400 ohms. Overhead line is having a surge impedance of 400 ohms. It's a case one. Case two I am calling here. Case two. Look. Case two. So, like this we have. Surge voltage injection is 100 kV. 100 kV. And next thing. We have a cable connection at the end. What we said earlier. I'm showing that cable connection at the end. It's a cable connected. Surge impedance of overhead line is 400 ohms. Surge impedance of cable, let's say 40 ohms only. Surge impedance of the cable is only 40 ohms. Next, look at the question. First case. 100 kV injected. That 100 kV is propagating towards the end. Reaching to the end, we are facing a substation. Substation. What will be the voltage experienced by the substation? At that instant when the 100 kV reaches to the junction, reaches to this junction. What is the surge voltage experienced by the substation? Is it 100 or more than 100? It will be 200 kV. Na? Substation means what you have inside. Substation means what you have inside. Transformer, right? Substation means we have a transformer inside. What is surge impedance of the transformer we have? That will be equals to infinite. Transformer surge impedance will be equals to infinite. So as it's infinite, it's acting as open circuit. Open circuit in the sense this voltage will become double. So I can say it is 200 kilovolts. Substation will be experiencing a voltage of 200 kV. 200 kV. Not only that. All of you listen to me. All of you listen to me. Listen to me. Just listen. 100 kV surge is propagating on the overhead line. Reaching substation means open circuit. Open circuit. Surge voltage becoming double. It is becoming 200 kV. Okay. What will be the overhead line voltage from that time? What will happen to overhead line voltage from that time onwards? From that time onwards, what will happen to overhead line voltage? Will it be 100 or it is also going to be increased to 200? Also increase it to 200. Also increase it to 200. That is the exact meaning of rise in the surge voltage. Not only junction voltage, the voltage backward line what we have also going to be increased to that value what we got. So 200 kV. Okay, next step. So you can see in this diagram now, 100 kV injected, 100 kV propagating, reaching to this first junction of line and cable. Reaching to this first junction of line and cable. So we have a surge voltage injection 100 kV. We have a refraction here V2 and we have a reflection here V1. Refraction V2, reflection V1. What is V2? Anybody please tell me what is V2 from this? V2. That is 2V into means 2 into 100 multiplied with R. See, is it required to consider the substation during the calculation at this junction? Is it required to consider the substation impedance while we are calculating at this junction? No. See, discontinuity was faced only by the line and cable. That's it, line and cable. After reaching to this junction, second junction, we should think about substation. Else it's not needed right now. So 2 into 100 kV, 2 into incident multiplied with 40 by 40 plus 400. 40 by 40 plus 400. Anybody please tell me this number how much? 200 into 40 by 440 means 1 by 11. 200 by 11. How much? 18.18 kV. Okay. 18.18 kilowatts. Okay. You see that 18.18 kV what you got now, that is propagated in the cable. Propagated in the cable, reaches to the end substation. Reaches to the end, that is substation. What is this substation voltage? What is that substation voltage? Double the value of 18.18. Double the value of 18.18 kV because it's a open circuit. And this number is 36.36 kV. That number will come to be 36.36 kilowatts. 36.36 kV. But you see in the earlier case, without keeping the cable, substation voltage is becoming 200 kV, double the value of incident. But now it is becoming only 36.36 kV. 36.36 kV. Getting the advantage of keeping the cable now? Getting the advantage of keeping the cable. All of you, please tell me. So this cable is going to act as surge absorber. This cable is going to act as surge absorber, which reduces the surge voltage magnitude and provides protection. Provides a sort of protection for the substation transformer or for the equipment what we kept above the cable location. Above the cable location. Okay. So I can write here. So else I will show like this better. So it is a transformer tank. You say, for example, it's a transformer tank. Okay. So like this, we have some cable connection. Let me call it's a cable. connected cable. So this cable is going to be called, as we said earlier, as a surge absorber. Surge absorber, and it protects substation or transformer from. It protects a transformer from surge voltages. Surge voltages. It protects transformer from surge voltages. Yeah. Surge voltages. Next thing. So what is the meaning of that short length of cable here? What is the meaning of that short length of cable? Okay, I will come to that. I'll come to that short length meaning maybe after some time. Yeah. So let's take up one more problem. I will come to that. I will comment on the length of that cable. Definitely. Yeah. So what's your question, Shruti? What if substation needs 200 kV? It's only providing 36 kV. We are discussing in the surge operation. We are getting a surge voltage. Surge current is rising. Definitely, Pallavi, surge current is rising. But how much time it is having? How much time it is what we call existing that surge current? Right? If the surge current again lies for a long amount of time, then it may cause for the damage of the winding. But it may last for a short amount of time only, so that it may not show a great effect for the winding. But listen please. But if there is a sudden rise in the voltage, because of that sudden rise, there is a chance of definite chance of having the insulation failure. Because generally for insulators, we used to have some unit. Like kilovolts per microsecond. We'll have some unit like kilovolts per microsecond, which will be indicating the sustainability of the insulator for the high rate of rise. If it is crossing certain limit, then there is a flashover or the damage of the insulator, definitely. Right? That's why we are concentrating only on the what we call surge voltages rather than currents. Sir, why I can multiply with the 2? Because surge impedance of transformer is infinite. After that, surge reaches to this junction, it will be looking at transformer. Transformer means it's an open circuit only, right? Yeah. So let's take one more problem now. So please read this. Look here. The ends of two long transmission lines, capital A and capital C, are connected by a cable B. The ends of two long transmission lines, capital A and capital C, are connected by a cable B. Okay. The surge impedances of ABC are 500, 70 and 600 ohms respectively. We'll take up that. A rectangular voltage wave of 20 kV magnitude. Rectangular voltage wave of 20 kV magnitude and of infinite length is initiated in A, travels to C. Okay. The reflected voltage into the cable B when the first reflected wave from the junction of B and C reaches to its former junction is dash K. Yeah. So it's not reflected actually. The refracted voltage. Refracted voltage. To the cable. Refracted voltage into the cable. So this is the exact statement given in the examination. This is the exact statement given in the examination. I think in ESC or civil services examination, they have given this type of question. This type of question. Okay. Go through it now. See, the ends of two long transmission lines A and C are connected by a cable. What we are saying. So I have to show two overhead lines first. Long lines, long transmission lines, two long transmission lines. This is A. You can say it is C. I am showing here. C, A and C. Two long transmission lines, A and C. And these are connected by a cable B. I am calling. B. I am calling here. B. Okay. Next thing. Just observe. Surge impedance of A, I think it is 500 ohms. Yeah. 500 ohms is surge impedance of A. Surge impedance of B is 70 ohms, I think. Surge impedance of C is 600 ohms. 500, 70, 600 ohms, respectively. A rectangular voltage wave of 20 kV magnitude and of infinite length is initiated in A, travels to C. Travels to C. Okay. Just look here. Look here. So on this A, we are going to inject a rectangular surge. Rectangular surge means you can see that rectangular surge in this manner. Rectangular surge or gate pulse. Gate pulse. 20 kV magnitude is the pulse magnitude. And the pulse width is a capital T I am showing. Pulse width is capital T we are showing. But what is said is, it's a rectangular surge of infinite length. It's a rectangular surge of infinite length. Infinite length in the sense, this time t tends to infinite, you can say. Infinite length in the sense, the time t tends to infinite. Time t tends to infinite means how this signal looks to be for you. As if the time t tends to infinite, how that signal looks to be for you. It will be step wave, right? It will be step voltage wave. Step voltage wave. So the injected surge, what we are talking now, injected surge, what we are talking now, it's a step voltage wave. Step voltage wave. So we have a step voltage wave of 20 kV. Step voltage wave of 20 kV. Step voltage wave of 20 kV. Okay, next. If the 20 kV propagating on this line A reaches to junction of A and B, reaching to the junction of A and B. So let me show or highlight that junction. Highlight this junction. This is a junction of A and B. Similarly, we have one more junction between B and C also. Between B and C also, there is a one more junction got formed. So it's a junction J1 you can call, and it was a junction J2 you can say. J1, J2. Okay, kindly listen. Voltage 20 kV propagating on A, reaching to this junction J1 first. Reaching to the junction J1. All of you listen to this. All of you listen to this diagram. Listen to this diagram. V is attacked to junction J1. There is a mismatch. Mismatch in the sense, you assume it is V1. V1 and V both are same. V1 and V exactly equal, 20 kV. 20 kV. There is no change. Just notation I am saying. It is causing for a refraction V2, and we have a reflection of V1. Sorry, V2, V3 you take, V3. Reflection V3, refraction V2. Whatever the V2 propagating on the B, propagating on the cable B, touching to this junction, touching to that junction, Again, we have a mismatch between the surge impedances, causing for a refraction V4, reflection V5. Reflection is V5. So it is V2 and I can say it is V5. V5. Okay. Now, whenever that V5 touching to this junction, J1 in the reverse direction, again experiences a refraction V6 and we have a reflection of V7. Reflection of V7. And where V7 touches to the junction J2, causing for a refraction V8, reflection V9. And again, V9 touching to this, we have a refraction V10, reflection V11. Like that, we get number of reflections and refractions. Number of reflections and refractions in this cable. Okay. I will make all your doubts clear. Just kindly look at this diagram. This diagram is going to be called generally Bevel's lattice diagram. It will be called as Bevel's lattice diagram. So he is a person, professor who invented this type of transient analysis. Bevel's lattice diagram. Okay, so let's continue with the question what they have asked exactly. Question. What they have asked exactly. Let's move back. See this. See, the refracted voltage into the cable when the first reflected voltage from the junction of B and C reaches to the former junction. That's the question. Look all of you. See, when the first reflected wave from BC junctions, what is the first reflected wave from BC junction? From this one you tell me. First reflected wave from BC junctions is what? Is it V1, V2, V3, V4, V5, V6, V7? Which one? V5. Good. See, whenever this V5, that's the first reflected wave from BC junction, reaches to former junction. Former junction means previous junction, right? Reaching to former junction is nothing but reaching to the previous junction. What is that previous junction? J1. So whenever this V5 reaches to J1 junction, what is a refracted voltage into the cable? What is a transmitted voltage into the cable? Tell me please. Which one? V6 or V7? V6 or V7? V7. V6 is transmitted into the line, right? V6 is a transmitted voltage into the line. But what is asking? Transmitted voltage into the cable. Into the cable what? V7. V7. So we have to calculate the value of V7. We have to calculate the value of V7. Even though it is a reflection for V5. Even though it's a reflection for V5, that's okay. But it is transmitted voltage into the cable. Transmitted voltage into the cable. That's the meaning here. That's the way of understanding exactly. So V7 value is our answer to be calculated. V7 is our answer to be calculated. Okay, what is V7? Okay, question, you leave it aside. We have to calculate V7. In this diagram, if we talk, in this diagram, V7 is reflection for V5. Reflection for V5. So first we should calculate V5. What is V5? Reflection for V2. Reflection for V2. So we should calculate V2. What is V2? Refraction for V1. Refraction for V1. Already you know V1, na? Already you know V1. With the help of V1, calculate V2, then V5, finally V7. That's our answer. That's our answer. Ashwin, don't modify the question. Sir, then the original statement of reflected in the question is much better, means for your understanding. For your understanding it is. Not in the original examination. Not in the original examination. The original examination, they have given the refracted voltage into the cable only. Yeah. Much better means don't modify the question according to our convenience. Look at the question, how they are asking in the exam. That's why I have modified that for you. So Arjun, where you have doubt, please kindly tell me. Where you have doubt? See, according to the statement what they have given, the refracted voltage into the cable when the first reflected wave from junction of B and C reaches to the former junction. Means after taking up these reflections and refractions continuously, why V7 I explained number of times. Yeah, look here, V1 I am taking, that is 20 kV, transmitted to J1 junction, finding some mismatch, causing for some refraction V2, which is not equals to V1. So we have a reflection V3. Whatever the V2 propagating reaches to J2, again there is a mismatch between the impedances. We have a reflection V5, refraction V4. Whatever the reflection V5 you have, V5, that will be reaching to previous junction. Okay. After reaching that to previous junction, again facing a mismatch between the surge impedances. So we get a reflection V7, refraction V6. And whatever the reflection V7 reaching to the next junction, obviously, because it is propagating to the next junction in the direction given. So again, we have a reflection, refraction. That reflection will come to J1 junction, again reflection and refraction. Like that, it will be continued for a good amount of time. Yeah. See, simply V2, V5, V7, V9, V11, all these things, whatever I am showing in the cable, these are voltages transmitted into the cable only. These are the voltages transmitted into the cable, irrespective of their name with respect to other terms in the diagram. Okay. Similarly, you see here, V1, V3, V6, V10, all these are voltages existing in the transmission line A. And here V4, V8, some other number, whatever you get. These are the voltages existing in the line C. Okay. These are adding to one another. Okay. To get V7, I said we have to calculate V5. We should go for V2. What is V2 formula? Simple. You have to consider only these two surge impedances. Incident is V1. So you have to take 2V1. So 2V1 into ZB by ZB plus ZA. 2V1 into ZB by ZB plus ZA. So I will write here V2. First I was calculating V2. So 2V1 into ZB by ZB plus ZA. Okay. So 2 into V1 is how much? It is 20 kV we said. So 2 into 20 multiplied with what is surge impedance of B? 70 by 70 plus surge impedance of A is 500. It will come in kilovolts. You tell me please, how much is this number? It will be 4.97. 4.91. 4.912 kV. That is V2. Next, we should go for V5. What is V5 here? Reflection for V2, na? Reflection for V2. How to calculate the reflector voltage? Incident voltage into impedance after the junction minus before the junction by the sum. You go with the formula. So it is V2 into ZC minus ZB by ZC plus ZB. Just go through this formula. V2 into ZC minus ZB by ZC plus ZB. So V2 4.912 kilo. What is ZC number? 600. ZB number 70 by it is 600 plus 70. in kV. In kilovolts. Yeah. Please tell me how much is this value? V5? V5, how much you are getting? 3.885 kV. 3.885 kV. Next thing. V7. V7 is again reflection for V5. V7 is again reflection for V5. What you should say that formula? See now at this junction, V5 will act as incident. V5 will be acting as incident. Now impedance above the junction ZA, before the junction is ZB. So you should call V5 is an incident into above the junction ZA, before the junction ZB. So you can get it is ZA plus ZB. So that V5 is 3.885. We have ZA minus ZB. ZA number 500. ZB number is 70. So you get this like 500 minus 70 by 500 plus 70. Direction of propagation is also important. In which direction it is reaching to the junction. Okay. How much is this number? This will come to be 2.93 kV. 2.93 kV. Yeah, I'm sorry. It's a different question. Second one, it is next question. Only this is a question for this problem, right? Those are not options. 2.93 kV is the answer. 2.93 kilovolts is the answer. So answer what we have to fill in the blank is 2.93. So I think most of you are clear about this one. Clear? Yeah. So next, let's look at that next question. Next question. Go through it. Yeah, see this. From the given data of the above question, the second impressed voltage on the C is, what is asking? Second impressed voltage on the line C. Second impressed voltage on the line C. Look here. What do you mean by that second impressed voltage on the line C? How many times I have to say for you? But V7 is reflected, na sir. You have asked refracted. I am saying you many times I have explained the same thing. We have to think about only voltage transmitted into the cable. Either it may be a reflection or refraction with respect to some other. What is transmitted voltage into the cable? That's it. Yeah. What is second impression? First impression, it is V4. C into C. First impression is V4. Second impression is V8. We have to calculate the value of V8. Second impressed voltage. Second impressed voltage is V8. V8. How to calculate that V8? How to calculate that V8? So it will be, so V7 is an incident now. Now the incident will be V7. So 2V7 into ZC by ZC plus ZB. 2V7 into ZC by ZC plus ZB. Yeah, so I'll write here. Second impressed voltage V8 is equals to 2V7 into 2 times of V7 into ZC by ZC plus ZB. ZC by ZC plus ZB. What you get this one? 2 into. What is V7? What is V7? How much is that value? So it will be 2.93. 2.93. What is ZC? What is ZC here? That will be 600. 600 by 600 plus, what is ZB number? 70 in kilovolts. Yeah, get this how much? That will come to be 5.247 kV. 5.247 kV. 5.247 kV. So close number you can choose that as D. Approximately 5.25 you can choose. Incident V7, no, to the junction. What is V5? V5 is this one, right? We have to check V7, this one. This is the incident. Now the incident is this. V7 is the incident. With respect to V7, you should find out the refraction. Yeah, okay. V7 plus V9 equals to V8. V8 value will be V7 plus V9. And this V4 is V2 plus V5. V4 is V2 plus V5. V7 you have to calculate. Yeah. So next, let's continue. Let's continue now. So till now what we have discussed is we have taken one distributed model, something like this. You no need to draw. One distributed model terminated with another distributed model having unequal surge impedance. This is Z1, Z2. And we are exercised how to calculate the reflections, refractions, all these things. But now, rather than one, if I have number of distributed models terminated by Z1, by this Z1 line, number of distributed models are terminated. Then how to calculate these refractions and reflections? Because maybe at the location of bus bar, one line, incoming line, gets converted into number of outgoing lines. One incoming line gets converted into number of outgoing lines. At the time, how to calculate the reflections and the refractions? That type of line we are going to call as bifurcated line. Bifurcated line, or you can say that as forked line. Okay, yeah. So let's see this. So the next heading in this topic, in this chapter is bifurcated line, or you can say forked line. Bifurcated line, or you can call it as forked line. Bifurcated line, or you can say this as forked line. Okay. See, as I am showing here, one incoming line and number of outgoing lines. This is the incoming line, you can say, having some surge impedance of Z1. And these are outgoing lines, you can say. Line 1. Or let's say only two. Line 1, line 2. That's sufficient. Same thing you can extend for any number of lines. Okay, that's what our interest is here. Okay, so this is a surge voltage injection B. Surge impedance of this line Z1, and this is Z2, Z2. Z1, Z2, Z2. Surge impedances. Okay, next thing. What is that current to be propagated here? After injecting a voltage V, how much is the current to be propagated? V by Z1. I is equal to V by Z1. That voltage V, current I, propagating on the line 1, reaches to this junction, it's obviously I can say this V comma I are incident. V comma I will be incident. V comma I are incident. See, definitely we get some reflection because of the what we call discontinuity. Like V1, I1, I will say as a reflection. V1, I1, we are calling as a reflection. reflection. Refraction, if you think, or you can say transmission. Transmission or refraction, you think. How many voltages you get in the transmission? How many transmitted voltages you are going to get? Please tell me. How many transmitted voltages you are going to get? Only one. Only one. Because this junction voltage what you get, that itself is experienced by both lines, right? Junction voltage, whatever we have now, the same voltage will be experienced by both lines, So we get only one refracted voltage, but there are two paths for the current flow. Two paths for the current flow means I can say here two refracted currents, I2 and I3. So I can say V2 comma I2 comma I3. These are refractions. These are refraction. V2 comma I2 comma I3. These three are going to be called as refraction. One voltage, two currents. One voltage, two currents. Okay, yeah. So next, let's continue to the calculation of this one. You assume that this is injected at a time t equals to 0 and we are reaching to this junction at a time t equals to capital. Now, with respect to that junction j at a time, with respect to junction j at a time capital T, we are going to construct the Thevenin equivalent model. Simple thing, simple thing. We are going to construct Thevenin equivalent model and then we try to find out V2, I2, I3 from that one. Then by using our regular formula of refraction equals to incident plus reflection, we find out the reflected quantities. Simple, right? I'll write with respect to the junction j at a time capital T, with respect to junction j at a time t equals to capital T, at a time t equals to capital T. First I will write refracted voltage, sorry, open circuit voltage. Thevenin model na. So open circuit voltage means first you remove these two lines, Z1, Z2. Z1, Z3 lines you remove and you write here open circuit voltage. Open circuit voltage. So VOC is equal to, that will be 2V. 2 times of incident. 2 times of incident. What is short circuit current in the similar way? Short circuit current, or you can say this as a Norton current also, ISC, it will come to be 2I. Short circuit current, or you can say this as a Norton current, that will come to be 2I. Now, Z Thevenin, if you talk, which is open circuit voltage to short circuit current, and this will be 2V by 2I, and the 2 and 2 will be cancelled out, and it will be V by I simply. What do you mean by that V by I? What do you mean by that V by I? That is Z1. That is Z1. Thevenin equivalent impedance is equal to Z1. Thevenin equivalent impedance is equal to Z1. Z1. Okay. Now, simply you draw the Thevenin equivalent model. Draw the Thevenin equivalent model. This is V Thevenin 2V. And you have here Z Thevenin, which is nothing but Z1. Z Thevenin, which is nothing but Z1. Okay, at the end, what we should keep now? At the end, what we should keep? Two surge impedances, Z2, Z3. Two surge impedances, Z2, Z3 will be in parallel. Will be in parallel. Two surge impedances, Z2 and Z3 will be in parallel. Like this, you can see. Right? So I'll call it is Z2 and Z3. And you observe this voltage is a refracted voltage V2, and these are the refracted currents we are going to show I2 and I3. Refracted currents we are showing as I2 and I3. Simple. Just by using this equivalent circuit, you try to find out the values of V2, I2, I3. this circuit used to calculate V2 comma I2 comma I3. V2 comma I2 comma I3. Okay. So if we have done, I will move to the calculations of these things now. Simple. See, Z2, Z3 will be in parallel. Z2, Z3 will be in parallel. You take up the equivalent impedance, simply like Z equivalent. This Z2, Z3 parallel combination you call as Z equivalent. Z equivalent. So I can say Z equivalent is equal to Z2 into Z3 by Z2 plus Z3. Z2 into Z3 by Z2 plus Z3. Okay. What is the refracted voltage V2? General formula now. General formula. It is 2V into Z equivalent by Z equivalent plus Z1. That's it. Okay. So refracted voltage V2 will be like 2V into Z equivalent by Z equivalent plus Z1. Z equivalent plus Z1. What is reflected voltage V1? That is nothing but refraction minus incident. Reflected voltage V1 is equal to refraction minus incident. That's it. That will be sufficient. Okay. If numerical problem is given, draw the Thevenin equivalent circuit like this, and you do your calculations in this circuit only. Sufficient. In this circuit only, you do the calculations. No need to remember the formulas. What is I2? I2, V2 by Z2. After calculating V2 value, V2 by Z2 will give I2. What is I3? V2 by Z3. V2 by Z3. Take up that. I2 is V2 by Z2. I3, it is V2 by Z. V2 by Z. What is reflected current I1? What is reflected current I1? That is total refraction minus incident. That is total refraction minus incident. Incident is I. Incident is I. Like this, you can calculate the things. Reflections and refractions you can calculate by using these equations. So this will be sufficient. Okay, next. So let's link up these things with the steady state. Let's link up these things with the steady state. Till now we have discussed about the transient conditions, transient things. Yeah. Look here, all of you. For example, I want to make some confusions a bit clear. Some confusions, whatever you have, I want to make it a bit clear. That's why I'm discussing this one. For example, we have a 250 kilometers length lossless line. 250 kilometers length lossless line. Lossless line. Operating at a frequency of 50 Hz. Operating at a frequency of 50 Hz. Inductance L per kilometer is 1 millihenry. Capacitance C is 10 nanofarad by kilometer. L, inductance is 1 millihenry by kilometer. Capacitance C is 10 nanofarad by kilometers. Okay. What is surge impedance and what is series impedance of the line? All of you please tell me. What is surge impedance of line? What is surge impedance? Surge impedance of line is what? Surge impedance of the line, ZC. That is nothing but root of L by C, na? Surge impedance is nothing but simply root of L by C. Whatever the number you get, that you calculate root of 1 millihenry by 10 nanofarad, that will give some value. Okay. What is series impedance of line approximately? All of you, please tell me. What is series impedance of this line? What is series impedance of this line? It's not 10 ohms. It will be coming like 316 something. Kindly check. Kindly check. Yeah, please tell me. Please tell me. I'm asking one very simple question. What is the series impedance of line? Series impedance of transmission line will be approximately series impedance of line, transmission line will be approximately equals to parameter B, generalized circuit constant parameter B. Yes or no? Generalized circuit constant, so-called parameter B. Yes. What is parameter B formula? What is parameter B formula? J, ZC, sin beta L. Lossless line. We said this is a lossless line. J, ZC, sin beta L. So this is a way of understanding. See, in the fourth chapter, so-called in the transient analysis, all the places, whatever the impedances I kept, Z1, Z2, Z3. What are these impedances? Z1, Z2, Z3. What are these impedances? Z1, Z2, Z3. Anybody? Tell me please. These are surge impedances of the respective lines. These are not the series impedances. Surge impedances of the respective lines. Those are not the series impedances. What is series impedance of transmission line wire? That is JZC sin beta L. JZC sin beta L. This clarity we should have. The difference between the surge impedance. Surge impedance is a characteristic. Surge impedance is a characteristic. Series impedance is the impedance of line what we are going to draw in the equivalent circuit of line. Okay? Yeah. Next thing. Next thing. Next thing. For example, we have reached to steady state. Let us say we have reached to steady state. Steady state again. I should discuss about two things here. Two things. One is a DC operation. DC operation. Second one, AC operation. Two things. DC operation, AC operation. After reaching to steady state, how is the behavior? How is the behavior? Okay. Look here. DC steady state. Steady state. DC steady state. Okay. You see, I am drawing one long transmission line. Long transmission line, something like this. This side, I will keep one DC voltage source. Okay. And surge impedance of this line is ZC. Surge impedance of this line is ZC, resistive, lossless line, moreover. Resistive, and moreover, the line is a lossless line. And this is a point of x equals to 0, and you take x equals to, that's your wish, whatever it is, x equals 0, x equals to here, doesn't matter. Yeah, at the end of this line, I am keeping one resistive load ZL. At the end of the line, we are keeping a resistive load of ZL. Okay, next thing. Kindly answer this. It is a sending end side voltage Vs, sending end side current as Is, receiving end side voltage VR, receiving end side current as IR. I already mentioned it is a steady state. I already mentioned that it is under steady state. It is under steady state. Okay, please listen. Please listen, all of you. Please listen. See, just think in the way of network analysis also. Stop writing. This line consisting some inductors and capacitors. Line consisting some inductors and the capacitors. We have a resistor in the circuit load. After reaching to steady state, you know that L is going to act as a short circuit, C is going to act as an open circuit for DC operation. For DC operation, after reaching to steady state, L will be acting as short circuit, C will be acting as open circuit, so that whatever the voltage and currents you have at the receiving end side, these values are same as sending end side quantities. Means we get VR equals to Vs, IR equals to Is, definitely. We get that VR equals to Vs and IR equals to Is, definitely. VR will come as Vs and the receiving and current will be same as the sending. Think all of you getting it? Yeah. So do you have any reflections under steady state? That's a question. Do you get any reflections under steady state? Yes or no? No voltage drop, na? No voltage drop. Else, if you have any doubt, simply what you do is all of you, please listen. All of you, please listen. All of you, please listen. If you have any doubt, simply what you do is find out ABCD of the line. Find out ABCD of the line. What is frequency of operation? What is frequency of operation? 0. Because supply frequency is 0, na? Supply frequency is 0. Frequency of operation is 0. Then what is beta? Beta of the line. Beta is omega root LC, right? Even though L and C values are existing, beta will be 0. Then what is cos beta L? 1. What is sin beta L? 0. And what are the ABCD of this line? What are the ABCD of this line? Under steady state. Also I mentioned under steady state. Once after coming to steady state, you go with ABCD. Go with ABCD. What is the ABCD? Cos beta L, J ZC sin beta L, J1 by ZC sin beta L, cos beta L. So you get 1, 0, 0, 1. If the ABCD are like this, you get VR, Vs are equal, IR, Is also equal, and you don't experience any reflections. No reflections under steady state, irrespective of ZL value. Whether the ZL equal to ZC or ZL not equals to ZC, doesn't matter. After reaching to steady state, no reflections. But during transient, if ZL is not equals to ZC, there will be a reflection. If ZL not equals to ZC, there won't be any reflection. I don't know whether you are clear this or not. All of you understood this? All of you understood this one? No reflections under steady state. Under steady state. Even though the value ZL is not equals to ZC. Even though the value ZL is not equals to ZC, there will be no reflections. But in transient, you will be having. Transient, you will be having. Transient state, you will be having it. Steady state, AC is very important for us to discuss. Steady state AC. Okay. So now, AC steady state. AC steady state. This is very, very important to understand also. To understand also, it is very, very important. Copy the same diagram. This one. So frequency existing, it's a non-zero number frequency. Beta will not be equal 0. I don't say it's a lossless line. I'll take this line as a general case only. The frequency of supply, some value. Okay. You please tell me, at some point X on the transmission line, we have a voltage of Vx and we have a current of Ix. At some point X on the line, at some point X on the transmission line, we have a voltage of Vx and we have a current of Ix. What are the expressions for this voltage and currents at any point? Voltage, you write sufficient voltage. What is the expression for the voltage at any point X on the line? This is steady state, it was lossless only, but load we have a resistor. Yeah, please tell me now. Please tell me. What is the expression for Vx here? Voltage at any point x under which condition? Which condition? Steady state. Means you go with ABCD. You can go with ABCD. Means what you can write here? Cos h gamma x into VR plus ZC sin h gamma x into IR. Cos h gamma x into VR plus ZC sin h gamma x into IR. Right, like that you have. Like that you have. Okay. Next. Let's continue. Cos h gamma x is, look, e power gamma x plus e power minus gamma x by 2 into VR plus sin h gamma x, e power gamma x minus e power minus gamma x by 2 into IR ZC. E power gamma x minus e power minus gamma x whole by 2 into IR ZC. Complete it quickly. Yeah. So you have to write this like some equation or some constant, whatever it is, some equation into e power gamma x into e power gamma x plus some other term into e power minus gamma x. Some term into e power gamma x plus some other term into e power minus gamma x. Tell me, e power gamma x coefficient will come like VR plus IR ZC by 2. VR plus IR ZC whole by 2. And here you will get VR minus IR ZC whole by 2. VR minus IR ZC whole by 2. Think all of you getting it? Please go back and check the previous classes, what you have done, if you have any doubt regarding the equation. This equation is perfectly written. Okay. See, actually in this Vx voltage term, e power gamma x, what we have here, it is going to be called as forward moving wave. E power gamma x is going to be called as forward moving wave. And this is a backward moving wave. Okay. So this wave is a forward moving wave. And this is a backward moving wave. Forward moving wave, backward moving wave. That forward moving wave, we are going to name it as incident. This is going to be called as incident wave. And this backward moving wave will be called as reflection. And this Vx is a resultant voltage at the point x, which will be named as refraction. Resultant voltage Vx, that is going to be called as refraction. Refraction is equals to incident plus reflection. Okay. So at what point we are discussing? I am saying point x now. So at this point x, let's call this is forward x, backward x, and this is a Vx. So at this point x, we have a forward moving wave of Vfx here, and we have a backward moving wave of Vbx, and the resultant voltage at this point is Vx. Resultant voltage at that point is Vx, you can see Vx. Yeah. Next, listen, please. When this backward moving wave is zero, or when this backward moving wave is non-zero, who is going to decide? This backward moving wave, is it zero or non-zero? Anybody please tell me. See, that is decided by this number VR minus IR into ZC, right? VR minus IR into ZC. Right. For example, if it is 0, so you can say VR equals to IR into ZC. VR equals to IR into ZC. I will write roughly. VR equals to IR into ZC. And VR by IR, if we take, that is ZC. What do you mean by VR by IR? ZL, where? VR by IR is ZL. Means my interest is to tell you, if the load impedance is equal to, if the load impedance equals to surge impedance, load impedance equals to surge impedance or characteristic impedance, then this backward moving wave will be 0 at all the places. At any point X you take, this backward moving wave will be 0 and the wave is not going to experience any reflection at any point on the transmission line. At any point on the transmission line. If this is not same, then the wave will be experiencing reflection at all the places on the line. At all the places on the line, including the load side. Which state we are discussing? Under which state we are discussing this one? Steady state or transient? Steady state only. Even at a steady state, there is a chance of getting the reflection from the AC operation. So I think all of you getting it. Let me conclude this one. If ZL equals to ZC, then voltage and current waves will not experience any reflections. Okay, next term. If that load impedance ZL is not equal to ZC, then waves will experience reflections at all the places on the transmission line. Reflections at all places on transmission line. Please be clear about this statement. Yeah, will not. Then the waves will experience no reflections. Waves will experience no reflections at all the places. Second one, at all places it will experience. Yeah, good. Just for my clarity, whether you have understood or not, for that I am asking one very simple question. Just listen. This is a model I have. I am asking one very simple question. Just look here. ZL and ZC are unequal. I am standing at this place. Look, all of you, please listen. Steady state, AC steady state. ZL not equals to ZC I have. Whether the wave will experience reflection at this place or not. I need your answer, yes or no. At this place, whether the wave is going to experience reflection or not. Tell me, please. Yes, definitely. Okay. Stop. Whether the wave is going to experience any reflection at this place or not. At this place, whether the wave is going to experience any reflection or not. Yes or no? Yes, it will be experiencing. See, even though, listen please, even though you say impedance before this point is surge impedance is ZC, above this point is ZC, we have equal. But in which state we are discussing? Steady state. In that steady state, it will look the whole impedance, effective impedance. It will be looking the effective impedance in the steady state. If that effective impedance is not matching with ZC, then definitely reflections will be happening. I think all of you getting this point. Clear? Yeah, at every point, the wave will be experiencing the reflection. So this ends the transient analysis, extended up to the steady state also. So we'll close at this point this chapter. We'll be starting the second chapter, that is voltage control and power factor correction. I will be giving the break at 9 a.m. I will be giving the break at 9 a.m., not now. Okay. Yeah. So let's start with this one. Chapter number 5, voltage control and power factor correction. We used to get questions with respect to the power factor correction in this chapter, mainly power factor correction. Of course, we start our discussion with the voltage control in the initial stage. Later on, we'll move to the power factor correction. Okay, you tell me in your understanding or in your view, why it is required to do the voltage control? Why it is required to do the voltage control? Yeah, tell me please, why we need to do the voltage control? For current also, we have reflections and refractions. I've discussed about only voltage. For current also, it will happen in the similar way. Imtiaz, you asked me your doubt in doubt session, please, kindly. Tell me, why we have to do the voltage control? Generally, we'll be experiencing some over voltages and under voltages. Over voltages and under voltages. To overcome the issues of that over voltage or under voltages, it is required to do the voltage control. See, particularly, if you keep that voltage within some band, then we can say that the performance of the load, or you can say apparatus, is satisfactory. Okay. For example, I will ask one very simple question. This is one system I have. Something like system having rated voltage 400 volts. Rated voltage of the system is 400 volts. Right now, at present, operating voltage is 398 volts. At present, operating voltage is 398. Can we call it as under voltage? Can we call that 398 as under voltage? Yes or no? Yes or no? Okay. For example, if I have a voltage of 380 volts, can we call this as under? Okay. For example, if you have a voltage 401 volt, is it a over voltage? Can we call it as over voltage? For example, if I have a voltage 405 or let's say 450 volts, can we call it as a over voltage? Yes or no? See, what is that condition to say the voltage as a over voltage or under voltage? Simply according to the standards. Voltage more than rated voltage is a over voltage. And a 400 volts rated voltage system, 401 is a over voltage. 402 is a over voltage. If the operating voltage is less than rated value, it is under voltage. That's it. 399 under voltage, 398 under voltage. But a over voltage or under voltage, for example, 401 and 398 today, these values are very close to 400, right? These over voltage and under voltage are very close to 400. If that's the case, it may not be required. It may not be required to go for control of the voltage. It may not be required to go for the control of that voltage. Okay. So when we have to do that voltage control means, particularly if the voltage crosses some tolerance band, maybe plus or minus 5%. Plus or minus 5%. For that condition only, we have to do the voltage control. Okay. So voltage control will be done generally if the voltage is out of this range. Be rated plus or minus 5%, I am saying. That's a tolerance band. First statement I am calling here, first statement. If the operating voltage is greater than 1.05 per unit, operating voltage is more than 1.05 per unit, or if the operating voltage is less than 0.95 per unit, less than 0.95 per unit, then voltage control has to be done. Voltage control has to be done. Voltage more than 1.05, less than 0.8. For these cases, you have to do the voltage control. It's not 12%, it will be 5%. Okay, tell me now, what are the various reasons to get the over voltage in the system? What are the various reasons to get the over voltage in the system? Please tell me. What are the various reasons to get the over voltage in the system? Yeah. See, actually, over voltage might be caused by some reasons we discussed earlier, lighting and switching. Look here, please. Lighting and switching will create over voltage. All of you listen. Don't ask me this question again. Right? So lighting and switching will be causing some over voltage in the system. But whenever we have this lighting over voltage or switching over voltage, are you going for correction of the voltage, means control of that voltage, or going for system protection? If you have an abnormal over voltage, are you going for protection of system or controlling of that voltage? We are going for protection, not for control. Not for the control. Means my interest is to tell you, we are going to do this voltage control only under steady state operation. Only under steady state operation. Only under steady state operation. So once if you say the term steady state, we can apply KVL, KCL, power equations, ABCD parameters, whatever it is we have studied in the steady state analysis can be used in this particular category. Following all of you, transient topic is over. Now again we entered into some sort of steady state analysis of the system. This voltage control and power factor correction is a type of steady state analysis only. Steady state analysis only. Now you please tell me, what are the reasons to get the steady state over voltages in the system? Reasons we have steady state over voltages. Reasons to have steady state over voltages. One reason is Ferranti effect. Ferranti effect. When this Ferranti effect will come for you for a condition of loading less than SIL, particularly for EHV lines and UHV lines. Particularly for EHV lines and UHV lines. Second one is due to leading power factor loads. Leading power factor loads will also cause for steady state over voltages. But among these two, Ferranti effect and leading loads, which is practical? Which is practical among these two? Ferranti effect is more practical compared to leading power factor loads. Leading power factor loads are not at all practical ones. More practical will be Ferranti effect compared to leading power factor loads. That's the meaning. Right? So steady state under voltages. What are the reasons to have steady state under voltages? Reasons to have steady state under voltages. Under voltages. Reasons to have steady state under voltages. It will be generally due to lagging load. That's it. Generally due to lagging loads. Lagging power factor loads. It's of two kinds, you can say. One, high quantity demand, high quantity. Next one is very low operating power factors. Two categories in this one, high quantity. And next one is low operating power factor. Low operating power factor. High quantity and then low operating power factors. These two under lagging condition will give the under voltages. Under voltages. Now, for example, we'll take up one system here. Simple system with a generator and connected to number of loads. Generator connected to number of loads. Look here, please. It is one voltage source or generator, you can say. And at the end of this generator, we have number of lines connected like this. Okay, number of lines, something like this. Showing at the end of each and every line, we have some load connected. We have some load connected. Okay. And this is our sending end side voltage Vs. Sending end side voltage Vs. Receiving end side, we have 1, 2, 3, 4 buses. So I can say it is VR1 voltage. You see, this VR1 and we have a voltage here as VR2 and this is VR3, VR4. Like this, we have some voltages you assume. Okay, we have a source, right? And we have bus 1, bus 2, bus 3, bus 4 voltages in this manner. See, listen, at present operating condition, high quantity means more power demand. That's the meaning. More power demand. More power demand. Yeah, listen, please, listen. At the present operating situation or present operating condition, it has been observed that bus number 4 voltage is very, very low in number. At the present operating situation, bus number 4 voltage is experienced as very, very low in number, but 1, 2, 3 are in the limits. 1, 2, 3 are in the limits, inside the limits. Okay, listen, please. Listen, all of you, please. Listen, all of you. I want to improve this voltage now. I want to improve this voltage. What are the various techniques available for us right now? How to improve this voltage? How to raise that voltage magnitude? One method, simply what I can say is, increase the value of Vs. You increase the value of Vs, automatically VR4 will go high. Na? If you increase the sending end voltage, definitely VR4 is going to be increased. How to increase VS? How to increase that VS? To increase that VS, we have to correct this excitation. We have to control this excitation. By using that excitation control, we are capable to increase the sending end voltage. By doing that, it is possible to increase the value of VR. This method of voltage control is going to be called as internal method of voltage control. Means by using our internal sources, means internal corrections. By doing that only, we are doing the voltage improvement. Okay, so voltage control methods. Voltage control methods. Voltage control methods. Voltage control methods. Yeah. First one we are saying in this, that is internal method of voltage control. Internal method of voltage control means I will be calling this as excitation control method sometimes. Excitation control method means simply by controlling the excitation of the alternator, it is possible to control the voltage magnitude at the required buses or at the buses. Simply excitation control. So by controlling excitation, mod V value, excitation of alternator unit. Excitation of alternator, mod V value can be controlled. Mod V can be controlled. I think many of you might have observed the disadvantage of this one. Many of you might have observed the disadvantage of this. What is the disadvantage of this one? Not only VR4, 1, 2, 3 also getting increased, right? Because of VS increment. Because of the VS increment, 1, 2, 3 also going to be increased. Means other buses voltages got disturbed. That's the disadvantage. Disadvantage of this voltage control method is other buses voltages got disturbed. Other buses voltages got disturbed. That's the disadvantage of this. Okay. Second method we are going to name it as external method. External method means, for example, there is a bus here. At this bus, we connect one compensator. At this bus, we connect one compensator such that only VR4 is going to be corrected. Remaining voltages will be unaltered. Remaining voltage will be unaltered. So by keeping some separate compensating equipment, maybe capacitor bank, reactor banks, whatever it is, right? By keeping them, it is possible to control the voltage only at the required buses, and remaining voltages will be unaltered in the system. Okay. Yeah. Second method is, I can say, external method. External method, right? So separate compensating devices are kept at the buses wherever it is required to control the voltage. Wherever it is required to control the voltage. Wherever it is required to control the voltage. Only at that bus we are going to keep the compensating device. Okay. So which method we have to follow now? Is it the first method or second method? Which method we have to follow? Second method we have to follow. External method of voltage control we have to follow from this. External method. Second method we have to follow. So called the external method. Okay, let's see here. Generally, in power system analysis or power system discussion, we find some terms we find some terms like real power, reactive power, Mancura voltage, frequency of operation, delta, excitation. These are various terms you can find. Real power, reactive power, mod V, frequency, delta, excitation. Among these 6 terms I have written, 6 terms. What are the terms dependent on each other closely? What are the terms depending on each other very closely? Very closely. That will be real power, delta. I think already we discussed about this now in power equations. In power equations, we discussed about this relation. P delta. One more term is a frequency. These 3 terms are coupled together, tightly coupled together, Remaining terms, Q, mod V, excitation. Those 3 terms are also tightly coupled together. So I can call Q, mod V, excitation. These 3 terms also tightly coupled together. And I can say these two groups are independent on each other. Independent groups under steady state operation. These 2 groups are independent groups under steady state operation. You please tell me which group you are interested to control. Which group you are interested to control? Is it group 1 or group 2? Which group you want to control? Group 1 or group 2? Group 2, na? Group 2. Because we have to control mod V, right? You have to control mod V in the sense, obviously, you should control the group. Controlling that mod V can be done by 2 ways. 1, controlling excitation. Second method, controlling the reactive power. Controlling excitation, controlling reactive power. Controlling excitation will fall in the category of method 1. Controlling excitation will fall in the category of the method 1. What is the next method? Controlling the reactive power. Means from this point onwards, what we'll say is, for mod V control, means voltage control, it is required to control the reactive power circulation in the system. It is required to control the reactive power flow in the system by providing some compensation, so-called the reactive power compensation. Okay, so I can say here, to control mod V, it is required to control the reactive power flow circulation. Right? To control mod V, it is required to control the Q flow circulation by providing Q compensation, reactive power compensation. By providing the reactive power compensation. See, before going for that reactive power control and all, first we should know, listen please. First we should know what are the various equipment they have in the system. Maybe starting from generator to different types of loads. What is the behavior? What's the behavior of each equipment with respect to reactive power? Is it absorbing the reactive power or delivering the reactive power? That property we have to study. Right? So after break, we'll take up each and every apparatus and we'll try to know what is the behavior of that apparatus with respect to reactive power. Is it delivering the reactive power or absorbing the reactive power? That we will make the comment. Then we will think how to provide that reactive power compensation for the voltage control. Okay. So have a break for 20 minutes break. So after this 20 minutes break, we will be continuing with that reactive power behavior with respect to apparatus. Yeah, thank you. So I have resumed the audio video on screen. So let's continue this table I am taking up. So on one side I will take name of the apparatus name. So is it going to act as sink of reactive power, or is it going to act as source of reactive power, or is it going to act as neither sink nor source of reactive power? Those three behaviors we are going to take up here, right? Neither sink nor source of Q. Neither sink nor source of Q. Okay, the first apparatus we are going to take up here, that is synchronous generator. First apparatus we are taking up here is synchronous generator. Synchronous generator. Yeah. Tell me please, is it a sink or source or neither sink nor source? Is it a sink or source or neither sink nor source? Please tell me. Yeah. Both. It will be acting as sink of Q as well as source of Q. Who is going to decide that? Means excitation. That will be decided by excitation. See, for under excitation conditions, it will be acting as sink of reactive power. Whereas for over excitation conditions, it will be acting as source of reactive power. And for certain normal excitation, it is neither sink nor source of reactive power, we can say. Okay? Yeah. So sink of Q for the under excitation condition. Under excitation condition, it will be acting as sink of Q. Source of Q for over excitation condition. Over excitation condition, it will be acting as source of reactive power. And neither sink nor source of Q for some normal excitation. For certain normal excitation, it will be neither sink nor source of reactive power. Okay. So along with that nature, we have to define what is the power factor. What is the power factor of generator if it is acting as sink of? What is power factor of generator if it is acting as source of? Similarly, in the other case. Yeah. Tell me please. During the operation of sink of Q, this generator is going to act as a leading power factor condition. So power factor of generator is leading. Power factor of generator is leading. See, I'll tell you, for example, just look here, all of you. Look here. This is one generator you take. Generator voltage source means it's a generator only. Connected to some RL load. Something like this. And you see this voltage at this place, voltage is V at an angle 0 degree. V at an angle 0 degree. And this load, what we have, RL load, is having certain impedance. It's some angle 5, let us say. Impedance angle is 5. Then how is this current? We can say current will be some magnitude I at an angle of -5. Current will be I at an angle -5. The same current will be delivered by source also. Same current will be delivered by the source also. This is one circuit, RL circuit. Second, I'll take RC circuit now. We have a voltage source connected to a load RC. Like this. And this point voltage, I will say again, V at an angle 0 degree. And this current, this RC load is going to draw leading current. Na? RC load will draw the leading current. So I can call I at angle plus phi. Same current will be supplied by the source also. Same current will be supplied by the source also. Same current will be supplied by source. Please kindly listen. Please kindly listen. This RL load, what we have here, RL load. What is the power factor of this one? What is the power factor of this RL load? Lagging or leading? Lagging or leading? Lagging. Because it is taking lagging current. Na? It is taking lagging current. So obviously power factor of this source, this load is cos phi lagging. Power factor of this load is cos phi lagging. What about the power factor of source? What about the power factor of source? Anybody? Is it lagging or leading? That's also lagging only. Power factor of source is also lagging only, because you should check what nature of current it is delivering here. If it is a source or generator, you should check what nature of current it is delivering. If it's a load, you should check what nature of current it is taking. What nature of current it is delivering? Lagging current. Na? So power factor of the source is also lagging. Power factor of source is also lagging. Simple thing. Next here you see. What is power factor of load? Leading. So I'll say it is cos phi leading. Cos phi leading. And you see this generator source delivering current. Delivering which nature of current? Leading current. So I can say this power factor will be leading only cos. Power factor of source is leading. Power factor of load is also leading. Both are in the same nature. Both are in the same nature. Next thing. With respect to reactive power, if you talk, with respect to reactive power, see this load, what we have, RL load, it will be absorbing reactive power. RL load is absorbing the reactive power. That's a convention. Then who has to supply that? Source should supply. Means source is delivering the reactive power. Means load is lagging load. Source is delivering the reactive power. Means load is lagging load. So power factor of load is lagging. Source power factor is also lagging only. Clear? Now you see here. Load, RC load, delivering the reactive power. Load is delivering reactive power means source is taking that reactive power definitely. Load is delivering the reactive power and source is taking that reactive power. In that perspective, source is taking reactive power means load is supplying that. Load is a capacitive load, or you can say power factor of load is leading. Then the source power factor also comes as leading in nature. I think all of you understanding this, what I said. All of you clear about this one? These diagrams, all of you clear? Please kindly respond. Yes. Yeah. So now you please tell me in this table, first I am saying generator. It is acting as sink of Q in the under excitation stage, absorbing reactive power. Now, please listen the sequence what I am saying. Generator is absorbing the reactive power. Who is supplying? Load is supplying. So load is supplying reactive power. Means what's the nature of load? Capacity. What's the power factor of load? Leading. Definitely generator power factor also comes as leading. Else you write here, generator delivers leading current. In this case, generator delivers leading current. So I'll write generator power factor is leading. Generator power factor is leading. Next you see here. In this case, generator will be delivering lagging current. Generator delivers lagging current. So I can say generator power factor is lagging. Generator power factor is lagging. Generator power factor is lagging. But here it will be operating at unity power factor. Generator delivers UPF current. UPF current. So I can say generator power factor is UPF. Generator power factor is UPF. Unity power factor we can experience for the generator. This is about the synchronous generator. Synchronous generator. Next, second element. Second element I will say induction generator. Induction generator. Second one, it's an induction generator. Induction generator. There's other type of generator we have. Tell me, is it a sink source, neither sink nor source? Induction generator, is it a sink source or neither sink nor source? What is the excitation provided for induction generator? 0. We don't have any excitation provided for the rotor field winding. So no excitation means 0 excitation. 0 excitation. 0 excitation condition means it will be definitely absorbing the reactive power, acting as sink of Q. There is no behavior of source as well as neither sink nor source here. There is no behavior of source as well as neither sink nor source. Okay, next, tell me. What's the power factor of this one? What's the power factor of induction generator? So if the generator, which current you should check? Is it a current delivered or current absorbed? If it is generator, what direction of current you should check now? Current delivered by generator or current absorbed by generator? Current delivered by generator, right? What nature of current it will be delivering? Definitely leading current. Because if it is absorbing Q, load is supplying it. Load is a capacitive load. If the load is a capacitive load, it will be taking leading current. So generator is delivering leading current. So obviously, power factor of this induction generator will be leading in nature. Leading in nature. So always, always, induction generator power factor is leading. Leading power factor means it will be delivering leading current. It will be delivering leading current. That's the mean. Leading power factor means it will be delivering the leading current. Fourth one. Sorry, third one. See, after generator, after that generator, what element will find? Generally, transformer. After generator, immediately we'll get a transformer. Transformer. Tell me please. Transformer. Is it a sink or source? Is it a sink or source or neither sink nor source? Definitely it will be acting as a sink of Q. Because of coil. We have inductive element, right? So inductive element means it will be always acting as sink of Q. There is no property of source as well as neither sink nor source. Transformer will be acting as sink of reactive power only. Sink of reactive power. Okay, next. Fourth one, after transformer, which element we find generally in the system? Transmission line wire. Transmission line wire. Yeah. So let's say transmission line, fourth one. Tell me please, is it a sink or source or neither sink nor source? Transmission line. Is it a sink or source or neither sink nor source? All the three. When it will be acting as sinker? When this line is going to act as sinker? For a condition of loading greater than surge impedance loading. We discussed about it. And for a condition of loading less than surge impedance loading, it will act as a source. Okay. For a condition of loading is equal to SIL, it will be neither sink nor source of reactive power. It will be neither sink nor source of reactive power. Neither sink nor source of reactive power. Okay. Next thing. So after line, again we find a transformer, behavior is same, it will be acting as sink of Q. Then let's enter into load. So fifth one I am saying, let's say induction motor. So it's a load, na? It's a load. Is it absorbing Q or delivering Q? Absorbing the reactive power. What's the simple reason? No excitation provided for the field winding. No excitation provided for the rotor field winding. No excitation provided. And it won't have a behavior of source and neither sink nor source. It won't have a behavior of source as well as neither sink nor source. Excitation is zero. It will be acting as sink of. What is power factor of this machine? What is power factor of this machine? Lagging, because it is taking lagging current, absorbing lagging current. So it will be operating at lagging power factor. Lagging power factor. Next thing. Fifth one you can say synchronous motor. Fifth one we are saying, sorry, sixth one, synchronous motor. Synchronous motor. Synchronous motor. Yeah, you tell me please. Is it a sink, source, neither sink nor source? In case of synchronous motor, is it acting as sink, source, or neither sink nor source? All. When it will be acting as sinker? When it will be acting as sinker? During under excitation stage. Under excitation stage. Please be remember about this one. Under excited machine will have a low voltage. Under excited machine will have a low internal voltage. If it's having a low internal voltage, definitely it will be absorbing the reactive power. Why? In the sense, reactive power will flow from higher voltage magnitude to lower voltage magnitude. Higher voltage magnitude to lower voltage magnitude. That's it. Okay. During overexcitation, it will be acting as source of reactive power. Overexcitation, it will be acting as source of Q. Neither sink nor source of Q for certain normal excitation. Normal excitation, it will be neither sink nor source of reactive. Tell me about power factor quickly. Transformer, there is no meaning of saying lagging power factor or leading power factor. It depends upon the load. Yeah, tell me first. Synchronous motor, under excitation, sink of Q. What's the power factor? Lagging power factor. Absorbing the reactive power, it's a load. So absorbing lagging current. So I can say lagging power factor in this condition. Whereas over excitation stage, it is delivering the reactive power, acting as a capacitive load. Acting as capacitive load means you can call it is leading power factor. And for normal excitation, you can say it is UPF. Yeah. So these are the behaviors of various apparatus existing in the system with respect to reactive power. See, before going for selection of any of these equipments for reactive or compensation in our system, first to tell me, what is a basic property? What is a basic property of an apparatus to be used as a Q controller or Q compensator? The basic property required for an apparatus to use that in the reactive power compensation means controllability. Controllability in the sense, for example, if you select one apparatus, if it is required to inject, let's say 20 MVR into system, if it's required to inject 20 MVR into system, it should inject only 20. If it is required to inject 25 MVR, it should inject only 25. Means my intention is to tell you how much amount of reactive power this compensator is going to inject. That should be completely in our control. All of you getting this word? That type of equipment we should select for the reactive power compensation. In the view of the control, can I choose synchronous generator? Can I choose the synchronous generator? Can I choose the synchronous generator? Yes or no? Yes, we have a control. By controlling the excitation, we We can control the amount of reactive power absorbed as well as the amount of the reactive power delivered. Induction generator? No. Why? It's absorbing Q, that's okay. Induction generator is absorbing the reactive power, okay. But you don't have a control. How much amount of reactive power it's going to absorb, that I can't control. Because excitation control is not there. And transformer also we can't use in that perspective. But you see, transmission line, by controlling loading, we are capable to command the amount of the reactive power absorption as well as delivery. But in the whole voltage control discussion, one point or one condition we have to maintain here is load should not be disturbed. Whatever the amount of load you have to supply, we have to supply. There is no chance of avoiding it. There is no chance of reducing the load here. So load is going to be maintained as constant in the complete voltage control analysis, right? Load will be maintained as constant. I'll write someplace here. Load demand maintained as constant. Maintained as constant. Or else you can say the load is going to be modeled as constant PQ load. Load is modeled as constant PQ load. Means the real and reactive powers demanded by the load are constant. Real and reactive powers demanded by the load are constant all the time. Okay, fine. So you can't vary the load value. That's what the comment we are making. Next one, induction motor can I use? Yes or no? Induction motor, no. What is the reason? What's the reason of not using induction motor? Because it's operating, it's that excitation is zero. There is no control. That's why we can't use the induction motor. Can I use synchronous motor? Yes, we have a control over the excitation. By that way, we can control the amount of Q absorbed as well as the amount of the Q delivered. Yeah, done. So, in the perspective of this discussion, which equipment we can use for that Q compensation or Q control means only two. One, it's a synchronous generator. Second one, it's a synchronous motor. But if you are using synchronous generator, it may fall in the category of internal method of voltage control. If you are using the synchronous generator, it may fall in the category of internal method. We have some disadvantages of it. That's why we can't use the first one, so-called the synchronous generator. We should go with only synchronous motor. So only one equipment right now we got, synchronous motor. Two applications. One, under excitation. Second one is a over excitation. Other than synchronous motor, we have shunt capacitor bank, shunt reactor bank, series elements. These things can be taken. Now, what I'll do is, I'll take the heading as basic voltage control devices available. Basic voltage control devices available in the system. I will list out all the things. So the next heading is basic voltage control devices. Basic voltage control devices available. Yeah. First one, shunt capacitor bank. First one is shunt capacitor bank. Second one, shunt reactor bank. Shunt reactor bank. Third one, series capacitor. Series capacitor bank. You can write this one also as bank, no issue. Series capacitor bank. Fourth one, synchronous condenser synchronous condenser, or you can call it as synchronous capacitor. Condenser, or you can say synchronous capacitor. Fifth one, synchronous coil. Synchronous coil, or you can call it as synchronous inductor or synchronous reactor. Any word you can use. Synchronous coil, synchronous inductor, synchronous reactor. Sixth one, synchronous phase modifier, or you can say phase advancer. Synchronous phase modifier, or you can say phase advancer. Modifier, or you can call it as phase advancer. Right? Synchronous phase modifier, or you can say phase advancer. We observe now in these total 6 devices given. 6 devices given. Yeah, this is the highest volume what I am giving to you, I think so. Vijay Sahu is the highest volume we are giving. Result base. First three equipment are static. There is no rotational body here. These are static. Static devices used for the voltage control. Static devices used for the voltage control. And the remaining 3 are having some rotating body. So these are going to be called as dynamic devices used for the voltage control. Dynamic devices used for the voltage control. Dynamic devices used for voltage control. Next thing. So before discussing about any one of these 6 devices given, right? So I'll discuss one basic concept of voltage control here. Very, very basic concept of voltage control. Just look here. For example, see, we have one voltage source connected to a line like this. At the end of the line, we have a load. Sending end voltage, I am calling Vs. Receiving end voltage is Vr. Current flow in this line is I. Impedance of that line is Z. Right? Impedance of the line is Z. Current flow in the line is I. This load, what we are keeping at the receiving end side, is a lagging load of high quantity. Is high power demand. Right? Lagging load of high power demand. Lagging load of high demand. Lagging load of the high power demand. Okay? Yeah. Next thing. So kindly look here. See, because of this high lagging load, high lagging power demand, obviously receiving end voltage will be less compared to sending end voltage. Receiving end voltage will be less compared to sending end voltage. Else better, I'll say the receiving end voltage is very, very low. This receiving end voltage magnitude expected to be very, very low. Very, very low. So we are experiencing a low voltage profile here. How to improve that voltage? How to control that voltage VR? What are the various techniques available to you? Don't tell me what device to be placed here. I also know by keeping shunt capacitor bank, voltage will increase. I also know that. But what is the basic technique? Basic modification what you have to make in this particular model to maintain that voltage at a good level. Yeah, tell me please. What's the basic modification you have to make here? One restriction you have here, load you should not change. Load you should maintain as constant. You should not modify the load. Second restriction, sending end voltage should be maintained as constant. You are not allowed to vary the sending end voltage. Means without changing sending end voltage as well as without changing the load value, how to improve that receiving end voltage? How to improve that receiving end voltage? First of all, you tell me why that receiving end voltage is coming as low in number? Why that receiving end voltage is coming as low in number? Because of voltage drop, right? because of voltage drop. See, simply if you control this voltage drop, definitely receiving end voltage is going to be controlled. So the simple technique of controlling the voltage in the system is controlling the voltage drop in the equipment, so called in the transmission line, right? Okay, so I can say to control mod VR value. So I can say voltage drop, so called I into Z shall be controlled. I into Z shall be controlled. Okay, you tell me now. Tell me now. Controlling I into Z. Controlling I into Z means there are two ways now. One, controlling current. Next one, controlling Z impedance. How to control current? How to control the current? Controlling the current means I will add one extra shunt element. I will add one extra shunt element such that definitely current flow in the line is going to be changed and that voltage drop is going to be changed. Okay, so first technique is current control technique. Current control technique. So in this case, a shunt connected device is added to control the reactive component of current, particularly reactive current only we are going to control. Added to control reactive current. Reactive current. A shunt connected device is added to control the reactive current. Okay. Next one. Controlling the series impedance. Controlling the series impedance. That you can say sometimes as series controller. Series controller. So second one, impedance control. Series impedance control, of course. We can call it as series controller. Series controller means a series connected device. A series connected device has to be added to control which element? Resistance or reactance now? Resistance or reactance? It is better to go with the reactance value, because reactance value we can increase as well as we can decrease by adding capacitor or reactor. Okay, so to control series reactance. So two controllers we have basically. One is a shunt connected device, shunt controller you can say. Second one will be series controller. Okay. See, for example, if you observe the devices what we have written, among all these things, except number 3, except this third one, remaining all 1, 2, 4, 5, 6 are shunt devices. Number 3 is a series controller. And 1, 2, 4, 5, 6 are the shunt controllers. Number 3 is a series controller which will be controlling the series reactance of the Yeah, so I'm sorry. Yeah, so let's look back to the devices what we have now. So these are 6 devices we have, 6 devices. Kindly look, see. So all these 6 devices either dealing with a capacitor or dealing with an inductor. That's it. In all these 6 devices, either we deal with an inductor or we deal with a capacitor. So first we'll see what is the behavior of that inductor and capacitor with respect to reactive power. Okay, yeah. So first I am taking up inductor. So already we studied about the behavior of inductor and capacitor with respect to reactive power, but still we are repeating that to give some final conclusion. Okay, look please. So I'll take in the case 1 here, we have a voltage source first. Voltage source and connected to some inductive load. Simply inductor, you can say. Inductor. So I have some voltage here. V at an angle 0 degree voltage. Current flow, it is I at an angle. How is it inductor current? Lagging current or leading current? Lagging current, na? So 90 degree lagging current. So you keep it is minus 90. Inductor current is 90 degree lagging current. So I am saying it is I at an angle minus 90 degrees. Now you keep that voltage and currents in a phasor diagram. Keep that voltage and currents in a phasor diagram. So this is the voltage phasor. This is the voltage phasor I am calling V. And how is the current phasor? 90 degree lagging. So I will be keeping that current phasor 90 degree lagging, something like this, right? 90 degree lagging. So it will be like this, you can say. Simple, very simple thing, very simple. What is real power P? Vi cos phi means cos 90. That will be 0. Real power equals to V into I into cos phi. That angle is 90 degree. So this value was 0. What's the reactive power Q? V into I sin 90 degree. So it will be simply Vi. That will be simply Vi. Reactive power Q equals to Vi sin 90. That will be Vi. Next. Same circuit I am repeating. Same circuit I am repeating now. In the second case, kindly follow it. Voltage source showing inductor. Showing inductor like this. Observe now, this voltage is V at an angle 0 degree. Voltage is V at an angle 0 degree. And you see this current, I at an angle minus 90, na? That current is I at an angle minus 90 degrees. Okay. But I want to take reverse current now. I want to take the reverse current. This direction current I want to consider. This direction current I want to consider means it's a minus of I at an angle minus 90. Minus of I at an angle minus 90 I should take. Listen please, all of you listen. Minus 1 we have na? Minus 1. That minus 1 we can take it as 1 at an angle 180 degree, or you can take it as 1 at an angle minus 180 degree. Both are same. 180 degree in the clockwise or 180 degree in the anti-clockwise, both will be same. So minus 1 can be written as 1 at an angle 180 or 1 at an angle minus 180. So if you modify this current negative of this one little bit, and you will be getting here as 1 at an angle 180 into I at an angle minus 90. So this will come like I at an angle 180 minus 90. 180 minus 90 means it will be plus 90 degrees. Which direction? Opposite direction. You are getting that current in opposite direction. Now, you show that voltage and red color current in the phasor diagram. voltage and red color current in the phasor diagram. Okay, check now, check. This is a voltage phasor I am taking up. Voltage phasor I am taking up like this. Voltage phasor. And how is it current phasor? 90-degree leading, red color current. Red color current is 90-degree leading. So you will be getting that current in this manner. You will be getting that current in this manner. So it will be 90 degrees. 90. Now, what's the real power and what's the reactive power? Real power, VI cos 90, 0. Real power, VI cos 90, 0. What's the reactive power? Q, VI sin 90. VI sin 90, that is nothing but VI. Q reactive power is VI sin 90, that's nothing but VI. VI. So I think all of you getting this? Yeah. Now, very simple thing, very simple thing. In the first case you can see, it is absorbing 0 real power and absorbing VI amount of reactive power. In both cases, real power is 0. Both cases, real power is 0. Just think about the reactive power. Think about the reactive power, sufficient. Direction of current, you check. Direction of current. It is into the inductor. Into the inductor. Means this inductor is absorbing a reactive power of VI. Inductor is absorbing a reactive power of VI. But in this case, red color current is outward. Red color current is outgoing. So I can say that inductor is delivering a reactive power of VI. Second case, what we are saying? Inductor is delivering a reactive power of VI because of current is outward from the inductor. Current was outward from the inductor. Which statement is correct now? Which statement is correct here? Inductor absorbing reactive power or delivering reactive power? Which statement is correct? Both are correct, right? Both are correct. Inductor is absorbing Q is correct. Delivering Q is also correct. But listen to me, listen. But we should show some difference, right? Same device, I can't say it is absorbing, delivering. We should show some difference in the wording. Listen. Which type of current it is absorbing? All of you please tell me. Which type of current it is taking or absorbing? Which type of current it is absorbing? Lagging current it is absorbing. Lagging current it is absorbing. So I will say inductor absorbs lagging reactive power. Inductor absorbs lagging reactive power. L absorbs lagging reactive power. Inductor is absorbing the lagging reactive power. Okay. Tell me please. Which type of current it is delivering? Which type of current it is delivering? Delivering which type of current? Leading current. Leading current it is delivering. Yes or no? Leading, Aishwarya. It will be delivering leading current. Delivering leading current means I will say inductor delivers the leading reactive power. L delivers leading reactive power. Leading reactive power. So simply the nature of current, lagging or leading, is added to reactive power term. Nature of current. First case lagging current, I said lagging. Second case leading current, I said leading. That's it. Simple, very simple. Very simple. Okay. Now let's think about the capacitor in the similar lines, and then we will make some conclusion. Capacitor. Capacitor, I am taking a capacitor. Okay, first one. So we have a voltage source here. And I will show one capacitor like this. Voltage is V at an angle 0. What nature of current the capacitor will absorb? What nature of current the capacitor will be absorbing? Leading current. It will be taking leading current. So I will say here I at an angle plus 90 degrees. I at an angle of plus 90 degrees. Okay. Next thing. Let us show that voltage and currents in the phasor diagram again. Voltage V at an angle 0. Voltage V at an angle 0. Yeah. So it is voltage V. And leading current we have I at an angle 90 degrees. Like this, we have current I at an angle 90 degrees. I at an angle 90 degrees. Now you take up the real power and reactive force here again. What is real power P? VI cos 90, 0. VI cos 90, 0. What's the reactive power Q? VI sin 90, that will be equals to VI. VI sin 90, that will be equals to VI. First one. Okay, second one. Second diagram means the same diagram I will repeat with the reverse of current. Same diagram we are going to repeat with the reverse of current. Second one. Same diagram. We are repeating with reverse of current. Yeah. So I am showing that the current direction in this way. Current direction in this way. Negative of that current we should take na. So it's minus of I at an angle 90 degrees. Minus of I at an angle 90 degrees. What that minus? Minus 1, minus 1. 1 at an angle 180 you write. Else 1 at an angle minus 180. That's your wish. Anything you can write. So I'll write 1 at an angle minus 180 multiplied with I at an angle 90. So if you calculate it, you get this like I at an angle minus 90 degrees. You will get that as I at an angle minus 90 degrees. Yeah, I at an angle minus 90. Now, you show that voltage and currents in the phasor diagram. Show that voltage and currents in the phasor diagram. So this is the voltage phasor first. We have voltage phasor like this. How is it current delivered by capacitor? Which nature of current the capacitor is delivering here? Lagging current is delivering. Capacitor is delivering lagging current. Capacitor is delivering lagging current. So you can get that current in this manner. And this angle we are showing as 90 degrees. And what's the real power? VI cos 90, 0. VI cos 90, that will be 0. What about reactive power? VI sin 90, that will be VI. VI sin 90, that will be equals to VI. Reactive power is VI sin 90, that will be equals to VI. Okay, now you tell me again. First case, capacitor absorbing reactive power or delivering reactive power? First case, capacitor absorbing Q or delivering Q? Absorbing Q. Second case, delivering Q. Which is correct? Capacitor, is it absorbing Q or delivering Q? Both are correct. Both are correct. But to show the difference, I will be adding the term lagging or leading to the reactive power. You see here in the first case, capacitor taking leading current means absorbing leading current. Absorbing leading current means I can write capacitor absorbs leading reactive power. Capacitor is absorbing the leading reactive power. Second one, capacitor delivers the lagging reactive power. Capacitor delivers lagging reactive power. Capacitor delivers the lagging reactive power. Okay. One more thing. See, before looking about all these things here, yeah, yes, it will be working with only reactive power. It won't deal with real power at all. So always Q in the same direction of current. Yes, obviously, Bhavani. Yes. Listen, please. So capacity is absorbing leading Q, or else you can say capacity is delivering the lagging reactive power. I will ask you one very simple question. Before discussing about this type of analysis of inductor and capacitor, if somebody asks you in a general way, inductor and capacitor, what's the behavior of these two with respect to reactive power? Tell me please, inductor, absorbing Q or delivering Q? Generally, a general word I am saying, general word. Inductor, absorbing Q or delivering Q? Absorbing Q, that's it. Inductor is absorbing Q. What about capacitor? Capacitor, is it absorbing Q or delivering Q? It will be delivering Q, that's it. See, if I say in a simple word, inductor is absorbing Q, capacitor is delivering Q, what nature of Q is that? What nature of Q is that? Inductor absorbing lagging Q, capacitor delivering lagging Q. Following all of you. So generally, if somebody says maybe in textbook or in the examination or anywhere, simply if they say reactive power, which reactive power you should consider that? Lagging reactive power only we have to consider it. Because we made a convention. That inductor is absorbing Q, capacitor is delivering Q. Based on that, you implemented the complex power equation as S equals to V into I conjugate. S equals to V into I conjugate. So complex power equation, already we have derived it. Complex power equation, S equal to V into I conjugate. V into I conjugate. So in this equation, convention is L absorbs Q, absorbs the reactive power, C delivers the reactive power. Delivers the reactive power is a convention. So again you write in this equation, Q in the sense lagging reactive power. In the sense it is lagging reactive power only. Q in the sense lagging reactive power only. So I think all of you getting that link up what I said? All of you getting that link up between that complex power equation, convention and nature of reactive power. Nature of reactive power. And one more word what I want to tell for you is one more word. Any apparatus, please listen, any apparatus, if it is acting as sink of lagging Q, maybe inductor you take, doesn't matter, inductor. It is a sink of lagging Q, na? Sink of lagging Q. Same apparatus will act as source of leading Q. Same apparatus will act as source of leading Q in the other way. If any apparatus acting as source of lagging Q, same apparatus will act as sink of leading Q in the other way. Following all of you. So that comment also I would like. So a sink of lagging reactive power acts as source of leading reactive power. Source of leading reactive power. Similarly, a source of lagging Q acts as sink of leading Q. Simple. A source of lagging Q acts as sink of leading Q. So these are some simple conditions we can experience. So let's take up some problems. Is this visible to you? Yeah, so let's take up the first question. First question. Is very simple question to give you further more clarity regarding the reactive power, leading nature, lagging nature. Yeah. Just look at this. See that. Which of the following apparatus will inject leading wires into the system? Which of the following apparatus will inject the leading wires into the system? Number one, induction generator. Number two, under-excited synchronous generator. Number three, under-excited synchronous motor. Number four, over-excited synchronous generator. Five, induction motor. Just go through it. Yeah. So I'm sorry. I'm sorry. Just go through it now. Go through it. See this. See, actually, we have five apparatus. Among these things, which apparatus will inject the leading wires into the system? Leave that question aside. Leave that question aside. First, you try to remember this one. Try to remember this one. Under-excited machine. Under-excited machine will act as sink of reactive power. Over-excited machine will act as source of reactive power. Just listen these statements. Under-excited machine acts as sink of reactive power. Sink of reactive power means sink of which reactive power? Sink of reactive power means sink of which reactive power? Lagging or leading? Lagging only. Lagging. Over-excited machine acts as source of reactive power. Lagging or leading? Lagging. Again, it is lagging. Both are lagging only. Sink of lagging Q, source of lagging Q. Okay. Now, just what you have to understand is among these five apparatus given, which are over-excited, which are under-excited. That's it. Which are over-excited, which are under-excited. Yeah. Tell me please quickly. These are the five apparatus. Induction generator. Over-excited or under-excited? Under-excited. No excitation. Next. Under-excited. Already the name itself is under-excited. This name itself is under-excited. This is over-excited. And this induction motor is under-excited. You see now, 1, 2, 3, 5. These 4, 1, 2, 3, 5 are under-excited machines, which will act as sink of lagging Q. So these four apparatus will act as source of leading Q, source of leading reactive. Okay. Yeah. So I can say here 1, 2, 3, 5. These 5 are, so these 4 are under excited machines acts as sink of lagging queue. That implies acts as source of leading queue. So which is a correct option? We have to choose now. 1, 2, 3, 5 means correct answer will be D. Correct answer will be D from the options given. Yeah. So let's continue. See, till now, we said many times that voltage control will be done by you by doing the reactive power control or reactive power compensation. But we have not discussed any standard relation between them. Mod V value and reactive power. That relationship we have not discussed till now. That relation we will study, then we'll take up each and every apparatus separately and we'll discuss about it. Okay? Yeah. So let's continue now. Let's continue. So I'm going to take up the relationship between mod V or receiving end voltage also you can say mod V and net reactive power. Or you can call sometimes as QS, or you can call this as sometimes QS. Net reactive power, or you can say this as QS. Relation between mod V and net reactive power, or else you can call it as QS. Okay. Very simple relation. We have some sending end side bus, transmission line wire, and this is a receiving end side bus. We might be having some load, whatever. Receiving end voltage is mod VR at an angle 0. Sending end voltage is mod VS at an angle delta. Sending end voltage we are showing as mod VS at an angle delta. Mod VS at an angle delta. All of you clear about lagging leading concept? Lagging Q, leading Q concept? If they didn't say, is it a lagging Q or leading Q, which Q we have to assume? Lagging Q only. Clear? Yeah. So let's continue. We are considering this line only with JX. There is no resistance as well as there is no shunt element. Mod VS at an angle delta, and receiving end side we have mod VR at an angle 0. This is the voltage what we need to control, mod VR. And we have to find relationship between net reactive power or else sending and reactive power. This is the sending and reactive power QS. So between this QS and mod VR, we should get the relation. Between this QS and mod VS, we should get the relationship. Simple. You write the QS equation. That itself will give the relationship. Okay. What is QS equation? Please write it quickly. What is QS equation? What we can say QS? At which bus we are standing? Sending and bus, na? So we should write mod VS by X first. Sorry, we have a network issue. So is it audible? Audio, video is clear now? Audio, video, is it clear? Yeah. Okay, fine. Listen. Sending and reactive for QS, na? At which bus we are standing? Yes, this is a location. So you should write mod Vs by X. Direction, S to R. So you should write mod Vs minus mod Vr. Reference, S itself is a reference because that's the bus we are standing, right? Wherever the bus you are standing, that you should take as reference. Vs you should keep as it is. Vr replaced with Vr cosine of angle. So Vr cos delta. Like this you should say. Okay. Now we will be making an assumption that this delta is very low angle, maybe 10 degree like that. So if that is very low, cosine of that angle is very close to 1. So let delta is small angle. Delta is a small angle. So I can say cos delta, it will be approximately 1. Cos delta approximately 1. So if I keep that cos delta approximately 1, so QS will come approximately mod Vs by X into mod Vs minus mod Vr. Okay. So QS is approximately equals to mod Vs by X into mod Vs minus mod Vr. Like this we can write. You call this is equation number 1 for time being. Call that as equation number 1 for time being. Okay, now I can write here. QS is proportional to from this. Some conclusions I will write. Then I will come back with the equation 1 and I will continue. QS is proportional to mod Vs minus mod Vr. QS proportional to mod Vs minus mod Vr. Or else you can say QS is proportional to that mod Vs minus mod Vr voltage gap. Approximately, not exact one. Approximately proportional to voltage drop also. Voltage drop, you can say. Yes, sometimes you see, you divide this with mod Vr, multiply with mod Vr. Divide with mod Vr, multiply with mod Vr. What you get now? Mod Vs minus mod Vr by mod Vr. That you call as a voltage regulation. Voltage regulation. So QS is proportional to voltage difference, or you can say voltage drop, or you can say proportional to voltage regulation. Let's continue with one. Let's continue with equation number 1. This Vs by X we have na, that you send to other side. Vs by X you send to other side. So it will come X by Vs into QS. X by Vs into QS. So I'll write from equation number 1. From equation number 1, X by mod Vs into QS, it is approximately mod Vs minus mod Vr. X by mod Vs into Qs is approximately mod Vs minus mod Vr, you can say. So from this one, receiving end voltage mod Vr is equal to mod Vs minus X by mod Vs into Qs. Receiving end voltage mod Vr is equals to mod Vs minus X by mod Vs into Qs. Mod Vs minus X by mod Vs into Qs, you can say. Receiving end voltage mod Vr. So is it our heading? What's our heading here? Relation between mod Vr and Qs. This is what the relationship we got between that mod Vr and the Qs. It's an approximate relationship. In the examination, very rarely we have to use this one. Right? Strictly speaking, it's a 2-bus system problem. We have to go with the power equations, including delta. This is a Approximate equation only. Approximate equation. So you can observe now, as this QS value tends to 0, as a QS value tends to 0, you observe that VR and VS values are a bit close. A bit close. Okay. So as a reactive for QS tends to 0, you can say this VR value tends to VS. VR value tends to VS. Yeah. Next. So let's start with the first apparatus now. Shunt capacitor bank, we'll use it. This expression we are going to use further and further. First apparatus we are going to take up, that is shunt capacitor bank. Shunt capacitor bank. First apparatus. Yeah. Say this. See, basically it's a shunt element which is going to control the current flow in the transmission line. That's a basic change. After that, voltage improvement, power factor correction, all these things will be followed. That's okay. But basic modification is it's going to control the current flow in the line. Okay. Yeah. So I can write here. It controls reactive current flow in the line. Reactive current flow in the line. Controls the reactive current flow in the line. Okay. Next. Generally, this shunt capacitor bank will be used in order to raise the voltage magnitude. For example, if you have a low voltage at a particular bus, and you add the shunt capacitor bank, it will increase that voltage magnitude. That's the meaning, right? So it is used. It is used to rise or increase the voltage magnitude. Rise or increase the voltage magnitude at under voltage buses. Under voltage buses during steady state operation. During steady state operation. Steady state operation. During steady state operation. Okay. Let's take up two cases here. Case 1 without shunt capacitor bank. Case 2 with shunt capacitor bank. We will see how much magnitude rise in the voltage we are going to get after adding the capacitor bank. Done. Right. So I'll say case 1 here. Case 1. It is without shunt capacitor bank. Without shunt capacitor bank. See this. We have a source connected to one line. And we have a load at the end like this. Load. And this load, it's a lagging load basically. It's basically a lagging load. Power factor of load is cos phi L lagging. Cos phi L lagging. Power factor of load is cos phi L lagging. Next. We have some sending end voltage Vs, which is constant. Receiving end voltage VR. Receiving end voltage we have as VR. X is a reactance of line. Okay, next. Please listen. This load, what we have here, it is absorbing a real power of PL, absorbing a reactive power of QL. That load is absorbing a real power of PL, absorbing a reactive power of QL. Okay, else you write load in detail. P load and Q load in detail. Next, look here. Real power injection to this bus by the line is P load. because it's taking P load amount of real power, so it has to inject it. What is the reactive power injection? That will be Q load. Reactive power injection is Q load. P load and Q load. P load and Q load. Next, you think about this line. Think about this line. This line, it is absorbing some reactive power definitely. That line what we have here is absorbing some reactive power. So I can say this line is having a reactive power of Q. That line is absorbing a reactive power of Q line. Q line. Okay, now you please tell me what will be the real power supplied TS1 and reactive power supplied QS1. What are the values of TS1 and QS1? TS1 is directly equals to P load because there is no real power loss in the line. So PS1, P load both are equal. What about QS? QS1 here? QS1 is nothing but Q load plus Q line. Q load plus Q line. Okay, let me write. PS1 is P load value. QS1 is Q load plus Q line. Q load plus Q line. QS1 is Q load plus Q line. Now you try to write this mod VR1 equation. Just now we derived, right? That mod VR1 equals to mod VS minus X by mod VS into QS1. QS1 is this. That will substitute. So I can say mod VR1 is equal to mod VS minus X by mod VS into QS1 is Q load plus Q line. Q load plus Q line. But practically speaking, this Q line number is negligibly small compared to Q load. Q line number is negligibly small compared to Q load. Q line number is negligibly small compared to Q load. Okay, whatever it is. VS minus some number is VR1. VS minus some number is VR1. So definitely I can say VR1 will be less compared to VS. This is equation 1. You can say if you want. So from this you can confirm that VR1 will be less compared to VS. Receiving end voltage VR1 will be less compared to sending end voltage VS. Mod VR1 is less compared to mod VS. Fine. Next thing. I'll take case 2 with capacitor bank. Case 2 with shunt capacitor bank. With shunt capacitor bank. At the receiving end side. At the receiving end side, or you can say at the location of the load. At the location of load. Same diagram we are taking up. Right, and same lagging load we have. Lagging load with some real and reactive powers. P load comma Q load. Power factor of load is cos phi L lag. Power factor of load is cos phi L lag. Now we are adding that capacitor bank at this place. Capacitor bank we have added. And receiving end voltage at this place, change it to VR2. Sending end voltage is VS. Receiving end voltage, change it to VR2. Sending end voltage is VS. Line reactance we are saying as X here. Line reactance we are saying as X. Next, this capacitor, what we have, capacitor, it is injecting the reactive power. Delivering the reactive power, I'll show like this. Is injecting the reactive power of QSH capacitor. Capacitor bank is injecting a reactive power of Q shunt capacitor. Q shunt capacitor. And anyhow, this load is taking a real power of P load. Load is taking a reactive power of Q load. P load and Q load will be there as is. Same numbers. Now you see, what is the real power injection by this line? I'll show in a red color. What's the real power injection by the line into the bus? That is P load only, na? Real power injection will be P load only. P load. What about the reactive power injection? Anybody please tell me? What about that reactive power injection? See, we have two elements. This load is absorbing some reactive power of Q load. Capacitor bank is supplying some Q shunt capacitor. What's the net Q to be injected by the line? That is nothing but Q load minus Q shunt capacitor. Whatever the difference between the two we have, that should be injected by the transmission line. Why? So I can say it is Q load minus Q shunt capacitor. Q load minus Q shunt capacitor. Q load minus Q shunt capacitor. And your line is anyhow absorbing some reactive power of Q line. Line is anyhow absorbing some reactive power of Q line. Now you check at the sending end side. Now, what is PS2 and what is QS2? What is PS2? What is PS2? Nothing but P load. PS2 is nothing but P load. What is QS2? Q load minus Q shunt capacitor plus Q line. In your line is absorbing reactive power. Q load minus Q shunt capacitor plus Q line. Q load minus Q shunt capacitor plus Q line. Now you take up that mod VR2 equation. You take up. Mod VR2 equation you take up, which is mod Vs minus X by mod Vs into QS2. X by mod Vs into QS2. QS2 is what? Q load minus Q shunt capacitor plus Q line. Q load minus Q shunt capacitor plus Q line. Q load minus Q shunt capacitor plus Q line plus Q. Yeah. So now I will try to rewrite this one. Mod Vs minus X by mod Vs into Q load plus Q line. I have minus gets cancelled. You get plus here. X by mod Vs into Q shunt capacitor. X by mod Vs into Q shunt capacitor. This is that voltage mod VR2. Mod VR2 equals to mod Vs minus X by mod Vs into Q load plus Q line plus X by mod Vs into Q shunt capacitor. That is neglected. Okay, yeah, listen now. See, do you have any change in the Q line value in the case 1 and case 2? Q line. Do we have any change in the value of Q line from case 1 to case 2? There is a definite change. Why? In the sense, current was changed, right? Current value was changed. Because of change in the current value, definitely there's a change in the value of Q line in the case 2 to case 1. But already I said that Q line is negligibly small compared to Q load. As a Q line is negligibly small compared to Q load, Q line can be neglected and the summation will be more or less same. So this I am going to rewrite as mod VR1. This I am going to rewrite as mod VR1. Check back to the equation 1. Mod Vs minus X by mod Vs into Q load plus Q line. This is nothing but VR1 equation. So finally, what you can write from this is receiving end voltage mod VR2 equals to mod VR1 plus X by mod Vs into shunt capacitor bank rating. shunt capacitor bank rating. Okay, so from this you can observe that VR2 is greater compared to VR1. VR2 is greater compared to VR1. So receiving end voltage magnitude was increased, we can say. Receiving end voltage value was increased. Mod VR2 was greater compared to mod. How much is that magnitude rise in the voltage you get? How much magnitude rise you got means that is X by mod Vs into Q shunt capacitor. Okay, so I'll write in the next slide. Magnitude rise in receiving end voltage. Receiving end voltage due to that capacitor bank placement, delta Vc equal to mod VR2 minus mod VR1. Mod VR2 minus mod VR1, that will come to be X by mod Vs into Q shunt capacitor. Come to be X by mod Vs into Q shunt capacitor. Q shunt capacitor. X by mod Vs into Q shunt capacitor. That is the magnitude rise in the receiving end voltage to be expected. Magnitude rise in the receiving end voltage to be expected. Okay. So I will be asking one reverse question here. What is the rating of capacitor bank required from this one? To raise the voltage magnitude by some number. To raise the voltage magnitude by some number, what is the rating of bank required? Delta Vc into mod Vs by X. Rating of capacitor bank. Q shunt capacitor. Delta Vc into mod Vs by X. Delta Vc into mod Vs by X. That's the rating of the capacitor, shunt capacitor. Let's generalize this little more. Let's generalize this one little more. Yeah, look here. Look here, please. For example, we have some big power system network. I'll say it's a 400 kV network or 132 kV network. Better, I'll take this one. 132 kV network. 132 kV network. This is one particular bus we are staying. This is one bus we are staying, for which we have number of incoming lines and outgoing lines. Maybe like this. I have some number of incoming and outgoing lines like this. Listen all of this knowledge. At this bus, or with respect to that bus, there is some Thevenin impedance or Thevenin reactance measured. Okay, Thevenin reactance value. And you see, at this bus, I want to raise the voltage magnitude by some value, right? Delta Vc, voltage rise required. Voltage rise required. Delta V equal to some value, whatever it is, 5 kV, 4 kV, whatever, some number value. Some. Obviously, to raise that voltage by that magnitude, what I said, we have to keep one capacitor bank. We have to keep a capacitor bank at this place. And what is the rating of this capacitor bank? What is the rating of the capacitor bank means? Obviously, we should use this formula. Delta V, how much? 5 kV. Vs, how much? 132 kV. By what is that X here? What is that X? What is that X we should take? Anybody tell me, please? I already said you. So in this case, rating of shunt capacitor bank would be delta V, magnitude rise, and mod Vs means you take rated voltage only, mod V by what is that X we should call? Thevenin equivalent reactance with respect to that bus bar. Thevenin equivalent reactance with respect to the bus bar we should consider. So this is one type of generalization. This is one type of generalization. Delta V, rise in the voltage, mod V, rated voltage by Thevenin equivalent reactance, external. So I think all of you getting it. Okay. For example, this is case one. You take case. For example, in case two, for the same example, same thing. If ZTH X Thevenin only, but I'm writing it as Z Thevenin now. ZTH and VTH Thevenin voltage are given with respect to the bus bar. With respect to this bus bar, if the Z Thevenin value, V Thevenin value, both are given, then how to calculate that rating of the capacitor bank for voltage boost? How to calculate the rating of the capacitor bank for the voltage boost? Voltage rise required is delta V. Voltage rise required is delta V. How to find out it? Yeah, yes. Okay, see in this case, please listen. All of you stop writing. All of you please stop writing. This is the capacitor bank what we are adding now. What do you mean by this V Thevenin and Z Thevenin here? What do you mean by V Thevenin? What do you mean by V Thevenin? That is a bus voltage before adding capacitor. V Thevenin is nothing but bus voltage before adding capacitor. Z Thevenin is a Thevenin impedance before adding capacitor. Because capacitor is your load, right? Capacitor is your load in the analysis now, right now. So, without adding this capacitor, whatever the network we have, whatever the whole network we have, that we replace with a single voltage source in series with an impedance, so-called V Thevenin and Z Thevenin. Then, at the end, we keep that capacitor and we will see how to proceed further. Okay, the whole network converted into a single voltage source in series with impedance, ZTH impedance. And this is a bus bar at which we are interested to keep the capacitor bank. And at that place, we keep that capacitor. What we need, ZC you assume it, which is negative of capacitive reactance. Okay. And what is this resultant bus voltage we need here? What will be that resultant bus voltage? Anybody? What will be that resultant bus voltage? That is V Thevenin plus delta V. This value was VTH plus delta. V Thevenin plus delta V. That's the resultant voltage required in the bus. Yeah, done. So when we have to use the first one, when we have to go with the second one. First one when we can use? First one when we can use? If the V Thevenin value was not mentioned in the data, if they didn't give the value of V Thevenin in the data, then I can go with first one, delta V into mod V by X Thevenin. If they have given both V Thevenin and Z Thevenin, we should try a network like this and we should find out the capacitive reactance value by doing analysis. And then you can say shunt capacitor bank rating will be VC square by XC. VC square by XC. Yeah. Simple, very simple. We derive the equation for the capacitor bank rating. Delta VC into mod VS by X. Okay. Now, if it's a big network, In that big network, at one particular bus, we want to raise the voltage by some number. For that purpose, we want to keep a capacitor bank. What is the rating of capacitor bank is? We have two methods to find. The first method, if only Z-Thevenin is given, only Z-Thevenin is given. If only ZTH is given, ZTH is given, simply you go with the equation delta V into mod V by Z-Thevenin or X-Thevenin. But if V-Thevenin value is also given, V-Thevenin value is also given, then with respect to that bus bar, you convert the whole network into a single voltage source in series with the impedance, right? And then you keep that capacitor bank and find out that capacitor bank reactance, and VC square by XC will give the rating of the capacitor bank. Rating of the capacitor bank. Yeah, fine. So this is about calculation of capacitor bank rating. Capacitor bank rating. So let's move back. Let's look at the first line what we have written here. Shunt capacitor bank is going to control the reactive current flow in the line. Reactive current flow. Now we will see how that current is going to be changed with the help of one phasor diagram. We'll draw one phasor diagram. With the help of that, we'll see how that current is going to be changed. Yeah, look here. Phasor diagram. Phasor diagram. Phasor diagram. So I'll take two cases now. Case one without shunt capacitor. Case one without shunt capacitor bank. Just observe here once. This is a line. And we have a load here. We have a load. Yeah, we have a load. See, this load, it's a lagging load basically. Lagging load basically. I'll assume this voltage as our reference mod VR1 at an angle 0 degree. With reference of that, this load is taking some current, lagging current, like mod IL at an angle negative. That load is taking some current like mod IL at an angle of -5. At an angle of -5. Now you see, this is the supply current IS1. Supply current IS1, that is nothing but load current only. The supply current and load current both are exactly same right now. Okay. So I can call here IS1 is nothing but load current itself. So it is mod IL at an angle -5. That's a case one. Next, case two. Case two. Same diagram I will repeat, but I will add a capacitor. Right. So it's a lagging load. Lagging load. Let me add that capacitor here. This is a capacitor we have added up. And you see here, this load is taking some current of IL at an angle -5L. But you know, after adding that capacitor, this voltage value was changed to mod VR2 at an angle 0. Voltage value was changed to mod VR2 at an angle 0. Why? This capacitor current, it's a 90-degree leading current. Capacitor current is 90-degree leading current. 90-degree leading current it will take. And this is a net current IS2 bar, you write if you want. Net current is IS2 bar, and you can get it as load current plus capacitor. Load current plus capacitor current. Load current plus capacitor current, you can say. Load current plus capacitor current. Now, simple, very simple. First to take voltage reference, mod VR1 at an angle 0 degree reference to take. Listen, stop writing, just listen. Mod VR1 at an angle 0 degree reference. Put the load current. That is nothing but supply one current, IS1 bar. That's it. Second case. For that load current, add the capacitor current, 90-degree leading, you will get IS2 bar. Okay. So, and you have to compare how is that IS2 come with the IS1. That will tell you how is that current magnitude variation and phase angle variation. Based on that, we will make our comments. Okay. Yeah. Let's say here. First, voltage I am taking as a reference here. Voltage we are taking as a reference. So this is VR1 phasor, VR1. First, load current IL at an angle minus phi L here. Load current is IL at an angle minus phi L, something like this, I'll say. Okay. Just observe. This is IL and this angle is phi L. That is nothing but phi S1 also. Phi L is nothing but phi S1, initial power factor angle. And this IL can be written as IS1. IL can be written as IS1. IL can be written as IS1. Next, for this IL current, we are going to add IC bar. IC bar means 90-degree leading current. Capacitor current is 90-degree leading current. So like this, you can get the capacitor current, 90-degree leading current. Right? So I'm showing that here, 90-degree leading current, IC bar. IC bar. So after adding these two, you will get the IS2 current now. This is that IS2 current. This is the IS2 current. And this angle is phi S2. That angle is phi S2. Okay. Yeah. So let's continue. Let's continue with this. So now you can observe here. How is it IS2 magnitude with respect to IS1 magnitude? How is that IS2 magnitude with respect to IS1 magnitude? Tell me please. IS2 magnitude will be less compared to IS1. That is one observation. Magnitude of IS2 is less compared to magnitude of IS1. Not only that, if you think about this power factor angle phi S2, that is less compared to phi S1. Think about the power factor angle phi S2, that will be less compared to phi S1. And not only that, if you calculate the power factor cos phi S2, that is greater compared to cos phi S2. Cos phi S2 is greater compared to cos phi S2. So there is an improvement in the power factor, yes or no? After adding the capacitor bank, the overall power factor of system was improved. So I can write the overall power factor of system was improved. Overall power factor of system was improved. So now you see this capacitor bank is doing two duties. One, improving the power factor. Next one, raising the voltage magnitude. So if you compare these two, in the sense after keeping capacitor bank, both the things will happen definitely. Improving the voltage will happen. Improving the power factor also going to happen. But if you compare these two, improving power factor is more dominant as compared to improvement in the voltage by keeping a capacitor bank. By keeping certain rating of capacitor bank, improvement in the power factor is more dominant as compared to improvement in the voltage. That's why practically we are going to call this capacitor bank as power factor correction device. Power factor correction device. Okay. Yeah. So I can write here the improvement in power factor, improvement in the power factor dominates the improvement in voltage. Improvement in voltage. Improvement in voltage. So shunt capacitor bank can be called as R. shunt capacitor bank will be a practical power factor correction device. Will be a practical power factor correction device. Power factor correction device. Okay, shunt capacitor bank will be a practical power factor correction device. Now we will see how will be the rating of that capacitor bank. How will be the rating of the capacitor bank with respect to power factor correction? Power factor correction. Let's take a small heading like this. To improve the power factor, look here. To improve the power factor from a value cos phi 1 lag to some other value, let's say cos phi 2 lagging. To improve the power factor from cos phi 1 lagging to cos phi 2 lagging. Cos phi 1 lagging to cos phi 2 lagging. What is the rating of the capacitor bank required? That we are going to study. That we are going to study. I'll take two cases now. Two cases. P1 Q1. P1 Q1. You can consider here if you want. P1 Q1, PS1 QS1. These are the real and reactive powers. Real and reactive power supplied by the source. Supplied by the source. Real and reactive powers supplied by source without capacitor bank. Without capacitor bank. Without shunt capacitor bank, real and reactive power supplied by the source will be P1Q. Let us say P2Q2. Let us say P2Q2. Check here P2Q2. What is it P2Q2? These are the real and reactive power supplied by the source with capacitor bank. With capacitor bank. So real and reactive power supplied by source with the capacitor bank. With capacitor bank. Done. Here. What is the difference? How will be the values of PS1, PS2? PS1 is P load. What is PS2? Also P load. P1, P2 are definitely equal. That's one conclusion, small conclusion. P1 and P2 are definitely equal. What about P2Q? Sorry, Q1, Q2. Q1, Q1. Q load plus Q line. What is Q2? Q load plus Q line minus Q shunt capacitor. So Q2 is less compared to Q1, na? Q2 is less compared to Q1. Q2 is less compared to Q1. Not only that, Q1 minus Q2, if you take, that is nothing but rating of the capacitor bank. That is nothing but the rating of the capacitor bank. So Q shunt capacitor is equal to Q1 minus Q2. Q1 minus Q2. Okay, now I will be taking up relations between the real reactive force. Real and reactive force, then we will move with these equations. Simple, very simple. Real power equals to apparent power into cos phi. Real power is equals to apparent power S into cos phi. Reactive power equals to S into sin phi. Reactive power equals to S into sin phi. See, from the first one, S is equals to P by cos phi. S equal to P by cos phi, that you substitute here. Substitute that here. So you can get now P by cos phi into sin phi. So from this, Q will be equals to P into tan phi. P into tan phi. Sin phi by cos phi will come to be tan phi. P into tan phi. This is a relationship. This is the relationship what we have. And between real reactive apparent force. Real reactive apparent force. This was a relationship, and you got Q equals to P into tan. Q equals to P into tan. What is Q1? Q1 is nothing but P1 tan phi 1. What is Q2? It will be P2 tan phi 2. Then what is Q shunt capacitor? Q shunt capacitor is equal to P1 tan phi 1 minus P2 tan phi. P1 tan phi 1 minus P2 tan phi 2. What about the values of P1 and P2 now? Equal. You take it common. Will come to be tan phi 1 minus tan phi 2. Tan phi 1 minus tan phi 2. So this is the rating of the shunt capacitor. P1 into tan phi 1 minus tan phi 2. P1 into tan phi 1 minus tan. And if you keep this P1 in three phase, definitely Q shunt capacitor comes in three phase. Keep the real power P1 in three phase manner, you are going to get the rating of the capacitor bank also in the three phase manner. Clear? Yeah. So have a break for 15 minutes. After break, we do one problem on this one or two problems on this one. Then we'll start with the shunt reactor. Okay? 15 minutes break. I resumed the audio video on screen. Please kindly confirm once. Yeah. So I'll take up some problems in this capacitor bank rating calculation. Yes. See this first problem I'm going to take up. See this one. So at an industrial substation, with a 4 megawatt load, at an industrial substation with a 4 megawatt load, a capacitor of 2 MVR is installed to maintain the load power factor at 0.97 lagging. Okay. If the capacitor goes out of service, the load power factor becomes simple, very simple. See this, we have a industrial substation with 4 megawatt load. Let me show that one. So this is a industrial substation with the load demand. I'll say P load simply. It is 4 megawatt. 4 megawatt. Okay. Now we are connecting one capacitor bank here. That shunt capacitor bank, of course, that rating is 2 MVR, he said. Q shunt capacitor, that is 2 MVR. MVAR. Okay. See, actually the statement, they should give the overall power factor, not the load. They should give the overall power factor 0.97. You should say this overall power factor is 0.97 lagging. Overall power factor is 0.97 lagging. See, he said that capacitor bank is taken out of service. Whenever you take that capacitor bank out, what will happen to power factor? I mean, see, whatever the 0.97 given here, that is a power factor after adding the capacitor bank, means cos phi 2. Cos phi 2 value was 0.97. 0.97. Okay. Now, after removing the capacitor, that is a power factor without capacitor bank. Without capacitor bank means you should take up cos phi 1 number. You have to calculate the value of the cos phi 1. So what is the relationship between these two means? Simply, Q shunt capacitor is equal to, just have a look at this. We have said already, it is P1 into tan phi 1 minus tan phi 2 na. P1 into tan phi 1 minus tan phi 2. What is Q shunt capacitor? 2 MVR. What is P1 value? 4 megawatt. 4 tan phi 1. We don't know, that we need to calculate. Minus tan. What is phi 2? Phi 2 is cos inverse of 0.97. Phi 2 is cos inverse of 0.97. You please calculate this tan phi 1 from this one. And then phi 1 angle. Then finally power factor cos phi. Tell me please. So what's the answer for this? Kindly check the answer. So this, we may be getting something like 0.8 lag. Kindly check it. Kindly check that. It will be 0.799 or you can say close to 0.8 lag. You calculate these two numbers. Tan phi 1 you calculate from this one. Then phi 1, then cosine of the angle will give the power factor. Okay, done. Next thing. Please make it quickly. So we'll take up one more problem with respect to this power factor correction. One more problem with respect to power factor correction. See this. See, a three-phase induction motor rated at 400 volts, 50 hertz, coupled to a pump, running at a lower power factor of 0.6 lagging. Running at a lower power factor of 0.6 lagging. The input is 4.5 kVA. Input is 4.5 kVA. It is proposed to improve the power factor to 0.8 lag by connecting a delta connected capacitor bank. Find the value of the capacitance per phase. Find the value of the capacitance per phase. Very simple thing. We have an induction motor that is rated for 400 volts, 50 hertz. And that induction motor is coupled to a pump running at a lower power factor of 0.6 lag. Means whatever the 0.6 is said, that's the power factor of the induction motor simply. Power factor of the induction motor. And input is 4.5 kVA. Means the induction motor is drawing an apparent power of 4.5 kVA. See, it is desired to improve the overall power factor to a number 0.8 lag by connecting a capacitor bank. See this question. Solution I am saying. So this is one induction motor I have. Induction motor, right? So it's a three-phase induction motor. See, power factor of this induction motor, I'll say it is cos pi im, that is 0.6 lag. 0.6 lag. S induction motor, 4.5 kVA. 4.5 kVA. S induction motor is 4.5 kVA. Okay. And he said line to line voltage, it is 400 volts RMS, and we have a frequency of 50 Hz. Line to line voltage is 400 volts and frequency is 50 Hz. Okay. Now we are going to connect one delta connected capacitor bank here. We are going to connect one delta connected capacitor bank. Delta connected capacitor bank like this. And this capacitor bank will be adding to this induction motor. To this induction motor in this manner. Done. Okay. Next. Find the value of capacitance per phase. Means you have to calculate C per phase number. All capacitance are equal. All the three capacitance values are equal, and we have to calculate that number. See, it's a very simple question, of course. Simple question. Kindly see this. See, first we try to find out rating of the capacitor bank required. Because he said the overall power factor required to be 0.8 lag. Overall power factor required is 0.8 lagging. What is the initial power factor or without keeping capacitor bank? That is 0.6 lagging. 0.6 lagging. So first we try to find out what is the rating of the capacitor bank. By using that rating value, we have some regular formula like V square by XC. V square by XC, already voltage is given. By manipulating that, we'll try to find out the capacitance number. Now, what is the formula for the rating of the capacitor bank here? So that is P1 into tan phi 1 minus tan phi 2. Very simple question I am asking you. Very simple question. With and without addition of capacitor bank. With and without addition of capacitor bank. Real power drawn by induction motor will be remain same. Real power drawn by the induction motor will be remain same. So whatever the P1 value we said, that is nothing but real power drawn by the induction motor. Real power drawn by the induction motor. That is S induction motor into cos phi induction motor. Real power is S into cos phi, na? So S induction motor into cos phi induction motor. What is the S induction motor? 4.5. S induction motor is 4.5 into cos phi induction motor is 0.6. It will be coming in kilowatts. That will be coming in kilowatts. How much is this number? Anybody? 4.5 into 0.6, how much? 2.7 kilowatts. 2.7 kilowatts. All of you getting it? 2.7 kilowatts. Now, You substitute this 2.7 kilowatt in this one. One more thing. Is it a per phase value or three phase value? Tell me please. Is it per phase or three phase? Three phase, because S induction motor is three phase, right? So S induction motor is three phase means it will be three phase number. So you get Q shunt capacitor also three phase. So I can say in the next slide. So Q shunt capacitor three phase is equal to P1 number 2.7 three phase into tan phi 1, tan of cos inverse phi 1 is cos inverse 0.6, okay, minus tan of cos inverse 0.8, like this. Yeah, you please get this number, reactive power Q, how much? $1.568, somebody is saying. Kindly check once again. 1.575. You'll get this number. 1.575 units will be kVAR. Units will be kVAR. And what's the per phase value of this? 1.575 by 3. Q shunt capacitor per phase means 1.575 by 3. How much is this number? How much is this number in terms of kVAR? 0. Per phase number by 3. 0.525. 0.525 kVAR. Please kindly understand what I am saying now. Please kindly understand. These three capacitors combinedly should supply a reactive power of 1.575. Three capacitors should supply combinedly 1.575, and each capacitor should supply 0.525. 0.525 kVAR. What is the formula for the Q shunt capacitor per phase? Formula for the Q shunt capacitor per phase is simply, just have a look at this. Capacitor per phase voltage square, VC per phase voltage square by XC. VC per phase voltage square by XC. What do you mean by VC per phase? VC per phase is nothing but voltage across C per phase. Voltage across C per phase. Yeah, you please tell me in this diagram, what is that voltage across C per phase? What is voltage across each capacitor? Tell me please. What is the voltage across each capacitor? That will be 400 volts. That will be 400 volts. As it is in delta, line to line voltage will appear across each and every capacitor. So this value was 400 volts. Now, already you know Q shunt capacitor. Find out the value of XC from that. Find out the value of XC. So XC will be equals to 400 square by 0.525 K. K in the sense 10 power 3. 0.525 K. K in the sense 10 power 3. Okay. Get this number, please. XC. Okay. XC means you can have 1 by 2 pi F into capacitance. 1 by 2 pi F into capacitance. XC number how much? XC 304.76 we are getting ohms. And capacitance value if we calculate, it will be 1 by 2 pi into frequency 50 multiplied to 304.76. 1 by 2 pi into 50 into 304.76. Yeah. So please calculate this number how much? 10.45. 10.45 microfarads. You will get that number in micro. 10.44 microfarads. Choose that answer very close to that. You can go with A, option A. Correct option will be A. Correct option will be A. Okay, fine. Next. So let's think about the same question what I am asking you. Same question. Simple, very simple thing. Same question. I will ask in a sequence, of course, sequence. Listen, all of you, listen. A three-phase induction motor rated at 400 volts, 50 hertz, coupled to a pump running at a lower power factor of 0.6 lagging. The input is 4.5 kVA. It is proposed to improve the power factor to 0.8 lagging by connecting a delta connected capacitor bank. First question. What is the rating of the capacitor bank? Anybody please tell me. What is the rating of the capacitor bank? Tell me please. Tell me the number. What is the rating of the capacitor bank? 1.575 we should give the answer. We should give the answer as three-phase number. Three-phase number we should give the answer. Okay? Yeah. Next question. What will be the capacitance per phase value if the capacitor bank is in delta? See, whether the capacitor bank is in delta or star doesn't matter. Rating, I have to keep this number. Whether the capacitor bank is either in delta or star. You have to observe till this point, I have not mentioned whether the capacitor bank is star or delta in the calculations. While you are going for Q shunt capacitor per phase, again I said VC per phase square by XC. And VC per phase is voltage across C per phase. If it is in delta, 400. If it is in star, 400 by root 3. If it is in star, it will be 400 by root 3. And your capacitance value will be different. That observation you should make. Okay. If it is in delta, what is the capacitance value? That will be simply 10.45 microfarads. 10.45 microfarads. Okay, done. Next. What is the, listen carefully, answer this one carefully. What is the power factor of induction motor after adding capacitor bank? What is the power factor of induction motor after adding the capacitor bank? Is it 0.6 or 0.8? That's the question. Is it 0.6 or 0.8? It will be remains at 0.6 only. It is not 0.8. I am asking the induction motor power factor. That will be remains at 0.6 only. Overall power factor value is becoming 0.8 lag. But induction motor will be stays at 0.6 lagging only. This clarity we should have. So always we should say overall power factor of the system is going to be increased to 0.8. Maybe you can call, there will be some distribution transformer supplying this power, right? That distribution transformer power factor was increased to 0.8 lagging. 0.8 lagging. I think all of you getting this meaning? Yeah. Fine. So let's take up one more thing. It is there. We will see that problem. Yeah. Go through this question. Yeah, it's not, sorry. Shunt reactor. Okay, we will see that problem after completing shunt reactor. After completing shunt reactor, we'll discuss some more problems. Let's continue with the next element that is shunt reactor bank placement in the system. Shunt reactor bank placement in the system. Shunt reactor bank placement in the system. So again, it's a shunt element, as you said. It's a shunt element. So by the addition of this one, you know, the reactive current in the line is going to be controlled, right? So it controls the reactive current flow in the line. Reactive current flow in the line. It controls the reactive current flow in the line. Next thing I'm saying, controls the reactive current flow in the line. Next thing. See, the shunt reactor bank we are going to keep generally to reduce the voltage magnitude. At the over voltage buses. Means under steady state operation, at any bus, if you feel there is a over voltage, you connect a shunt reactor there, it will reduce that voltage magnitude. That's the meaning. Okay, right. So it is used to reduce the voltage magnitude, reduce the voltage magnitude, at over voltage buses, at the over voltage buses during steady state operation, during steady state operation, during the steady state operation, right? Next thing. So it's given apparent power only. They have given that as apparent power. He said in volt amperes, right? Volt amperes means that 4.5 kVA. That's apparent power. Yeah. Let's see again two cases here. One without shunt reactor, second case with shunt reactor. And we'll see how much is that voltage change we are going to get after adding the shunt reactor. Let's see here case one. Case number one. We have a source. Okay, and a line connected like this, and it's a load, right? Load. Just look here first. Look here. Sending end voltage, and we have receiving end voltage of VR1. Receiving end voltage of VR1. Yeah, please listen. Please listen. See, actually, the aim is first to show that there is a over voltage at the receiving end side. So I have to show that there is a over voltage at the receiving end side. Okay. After showing that there is a over voltage, next we will add one shunt reactor. We'll add one shunt reactor, and we will see. We'll see how much decrement in the voltage magnitude we are going to get. How much decrement in the voltage magnitude we are going to get, and then we will find out what is the rating of that reactor by extension of it. Okay, fine. See, generally, steady state over voltages will occur due to Ferranti. But you know that Ferranti effect we can show in either medium line model or in the long line model. We can show that Ferranti effect only either in the medium line model or in the long line model. But what model we are taking now? Only series impedance, only series reactance impact. So in this model, I can't show Ferranti effect, right? I can't show the Ferranti effect. So even though you are operating under no load, I can't show that this VR1 is greater compared to VS. So just for the study purpose, I am taking a leading power factor load at this place. I am taking one leading power factor load at this place. I think all of you getting this word? Leading power factor load we are keeping at that place. Yeah. Why we are keeping this leading power factor load? After keeping that leading power factor load, I will show that this VR1 is greater compared to VS. And by saying that VR1 is more compared to VS, in the very next step, I will keep one shunt reactor, and I will see how much decrement in the voltage we are going to get. That we will conclude further. Clear? Right. So next, I can say here, look here, please. Look here. Power factor is cos phi L leading you take, cos phi L leading, and I will say some real power injection, P load, and this is taking some complex power like P load minus J Q load. It is taking a complex power of P load minus J Q load. It is taking a real power of P load, and how much amount of reactive power it is taking now? Minus Q load, it is taking some reactive power. Taking a reactive power of minus Q load, and the line reactive power consumption is Q line. Line reactive power consumption is Q line. Next. This is PS1 and this is QS1. Same as earlier. PS1, QS1. What is PS1? P load. What is QS1? Minus Q load plus Q line. Just similar to the earlier discussions. You can say PS1 is P load value, and then QS1 is minus Q load plus Q line. Minus Q load plus Q line. But you know that Q line is very less compared to Q load. That Q line is very, very less compared to Q load. In that sense, that QS1 will be a negative number. QS1 will be a negative number. PS1 equals to P load, QS1 equals to minus Q load plus Q line, and this number is coming as negative number. Yeah. So now if you write that VR1 value, receiving end voltage, VR1, so that will be Vs minus X by mod Vs into QS1. So that is mod Vs minus X by mod Vs into QS1 is minus Q load plus Q line. Minus Q load plus Q line. This is negative value already. I mentioned this value was negative. So that minus gets cancelled out. Vs plus some number. Vs plus some number is VR1. So definitely I can say the VR1 is greater compared to Vs. So VR1 voltage is greater compared to Vs, sending end voltage. Receiving end voltage, VR1 is greater compared to Vs. Now I'll take the case 2 with the shunt reactor. Case 2, I'll show in the next slide better. Yes. Right. So next one we are going to take case 2. Taking up this diagram, we have a source connected to one line, and we have a load here, and we will be adding that shunt reactor at this location, shunt reactor. Yeah. See this. I am adding that shunt reactor at this place. This is a shunt reactor we are adding. Okay. So after adding that shunt reactor, this voltage value was changed to VR. And this voltage will be remains at Vs only. That voltage will be remains at Vs. And what's your load? It's a leading load with a power factor of cos pi L leading, and it's taking some real power of P load and reactive power minus JQ load, like this. Let's keep these things quickly in this diagram. So what about this reactor? It is absorbing reactive power. Reactor is absorbing a reactive power of Q reactor. Absorbing a reactive power of Q reactor. Now you see. What is a real power injection and what is a reactive power injection? What's the real power injection? P load only. Real power injection is P load. What about the reactive power injection? Two elements connected. Load taking a reactive power minus Q load. Reactor taking a reactive power of Q reactor. Summation of the two is a net injection. So Q reactor minus Q load it will come. Q reactor minus Q load it will come. Q reactor minus Q load. What about your line? What about your line? This is absorbing a reactive power of Q line. Absorbing a reactive power of Q line. Okay. Next. This is PS1. Sorry, 2. It is PS2 and this is QS2. PS2, QS2. What is PS2 number? Equal to P load. PS2 is equal to P load. What about QS2? Observe now, QS2 is what? Q line plus Q reactor minus Q load. Q line plus Q reactor minus Q load. Like this, you will get QS2. After getting the PS2 and QS2, let us take up that mod VR2 equation. Let's take up that mod VR2 equation. Mod VR. Right here, magnitude of the receiving end voltage mod VR2, mod Vs minus X by mod Vs into QS2. Na? QS2 I will rearrange. These things. Minus Q load plus Q line plus Q reactor. Like that, I am rearranging that term. I think it's okay. Minus Q load plus Q reactor, plus Q line plus Q reactor. Check that one, please. Check that one once, please. Think all of you getting this? Now let's divide this into two parts as usual we have done earlier. So it will be mod Vs minus X by mod Vs into it is minus Q load plus Q line. First term I am taking, and in the second term you will get minus X by mod Vs into Q shunt capacitor, Q reactor, Q shunt reactor. And you know the first two terms here, Vs minus X by Vs into minus Q load plus Q line. We have written here, na? That is VR1, equation 1. That is VR1. Whatever it is, this is simply VR1. So you can write receiving end voltage magnitude after keeping shunt reactor will be VR1 minus X by mod Vs into rating of the shunt reactor bank. Rating of the shunt reactor bank. And what is the conclusion we can make from this? What is the conclusion we can make from this? Means it is mod VR2 value less compared to mod VR1. Mod VR2 value less compared to mod VR1. Receiving end voltage magnitude was decreased. By how much? By how much? How much means that is X by Vs into Q reactor. So magnitude decrement in the voltage. Observe here, magnitude decrement in the voltage, magnitude decrement in voltage. So you can call it is delta VL here, is mod VR1 minus mod VR2, initial voltage minus final voltage. Na? Initial voltage minus final voltage. That is the decrement in the voltage. So it is same as previous equations we are getting, right? All of you, please check. Are you getting the similar equations? Delta VL is equals to X by mod Vs into Q reactor. Delta VL is equals to X by mod Vs into Q reactor. And in reverse, rating of the reactor bank is delta VL into mod Vs by X. Rating of shunt reactor bank. Rating of shunt reactor bank, right? It will be Q reactor is equal to delta VL into mod Vs by X. And in general, if you want to write, you take X Thevenin. In general, if you want to write, you can take it as X Thevenin also. XD. Okay. Next, Let us compare the power factor. Let's compare the power factor without shunt reactor bank and with shunt reactor bank once. Just look here, look here. Without shunt reactor, we have this model. I'll copy this model. See this quickly. To avoid that confusion, I am showing the models again. This is without shunt reactor. Without shunt reactor. Next. With shunt reactor. This model we have with shunt reactor. Okay. Observe, please. Observe here, please. Yeah. Tell me in the first case. What is the receiving and power factor? Cos pi r. You say cos pi r, receiving and power factor. So you know real power, reactive power. P load minus Q load. So it is simply P load by root of P load square plus Q load square. Root of P load square plus Q load square. Q load square means negative of Q load square. So you write it simply Q load square. Sufficient. Minus Q load also you keep no issue. Minus also you keep no issue. So P load by root of P load square plus negative of the Q load square. That's a cos pi r. Now you tell me in this case, after adding shunt reactor, what is cos pi r? What is cos pi r in this case? P load in the numerator. P load in the numerator by square root of what you get now? P load square plus what is that reactive power? Q reactor minus Q load, na? Q reactor minus Q load. So it will be Q reactor minus Q load. So else you write minus Q load plus Q reactor minus Q load plus Q reactor square. Yeah, could you please tell me now? Could you please tell me how is this denominator term in the second case compared to first case? You take 1 and 2. Cos pi 1, cos pi 2 to make that difference. To make the difference. Kindly tell me. How is the denominator in the second case? Less, na? Here you have minus Q load, means Q load square. But here Q load minus Q reactor square. Q load minus Q reactor square. So this is less. So denominator is less. And this cos pi 2 is greater compared to cos pi 1. Cos pi 2 is greater compared to cos pi 1. Means you have to observe that. Resultant power factor after adding shunt reactor bank was increased. Is it improving power factor of system or not? Whether the shunt reactor bank, is it improving the power factor of the system or not? Yes, it is improving the power factor of the system. But the load is a leading load. If there is a leading load and you add a shunt reactor, then it will definitely improve the power factor. That condition we have to apply. Okay? Yeah. So let's say shunt reactor bank improves the power factor, if the load is leading in nature. Okay, you tell me what are the practical loads in our system? Whether the practical loads are leading in nature or lagging in nature? Practical loads, which nature? Lagging nature, right? But practical loads are in lagging nature. But practical loads are lagging in nature. Okay, next thing. See, practical loads are in lagging nature. That's okay. Now I'll say, if there is a lagging load, shunt reactor is added. I have a lagging load and I am adding a shunt reactor. What will happen to overall power factor? It will decrease. Overall power factor will decrease. Means will this shunt reactor acts as practical power factor correction device? No, it is not a practical power factor correction device. Okay, so if shunt reactor is added across lagging loads or practical loads, then overall power factor will decrease. Then the overall power factor will decrease. Okay, so that implies shunt reactor is not a practical power factor correction device. Is not a practical power factor correction device. Power factor correction device. It is not a practical power factor correction device. Done? Not a practical power factor correction. Then what is the practical application of shunt reactor? What will be the practical application of the shunt reactor? It will be used to reduce the over voltage in the system under steady state operation. Means it will be used to reduce the Ferranti effect, right? So shunt reactor, it's going to be practically called as, it's a practical power factor, practical Ferranti effect control device. Practical Ferranti effect control device. Ferranti effect control device. You should not say the statement. At the starting, we said we have some devices, shunt capacitor bank, shunt reactor bank, series capacitor, and so on. Shunt capacitor we studied. It is taken as power factor correction device. Shunt reactor we studied. It's taken as Ferranti effect controller. So these are not used as voltage control devices. That's not the statement. These are voltage control device only. Voltage control device only. But practical application is a bit different. Even though you are saying that shunt capacitor bank is used to improve the power factor, will it become without rising the voltage magnitude? No, it will be rising the voltage magnitude as well as it will be improving the power factor. That's the way of understanding. You should not say that these are not voltage control devices. These are voltage control devices only, but practical application will be a bit different. That's it. Okay, yeah. So let's take some problems on this shunt reactor bank also. First one I'm taking up here. Check this or not. Yes, good. Check this problem once. Check this problem. Check this one, please. See that? So the ABCD parameters of a three-phase overhead transmission line are A equal to the 0.9 at an angle 0 degree, B 200 at an angle 90 degrees, C 0.95 into 10 power minus 3 at an angle 90 degrees. At no load condition, a shunt inductive reactor is connected at receiving end side of the line. To limit the receiving end voltage magnitude to be equal to sending end voltage magnitude, the ohmic value of the reactor is. Yeah. Practical, it's a variable compensation only, but some places we are using fixed also. That depends upon available available amount, or you can say that depends upon the economy what we have. That depends. For example, at some place it's not a essential place, but we need to keep some compensator. There the people might go for a fixed compensator. If it's not much essential, we may go for fixed. But at some places, if it is very essential to keep some compensators, at those places the people might be going for controlled compensators. Okay, that depends. Yeah. Next, let's continue with this problem. See, we have ABCD parameters of line. Okay, per phase. Next, operating under no load, that was clear from the question. At that no load condition, he interested to keep one shunt reactor bank at the receiving end side, such that no load receiving end voltage magnitude, sending end voltage magnitude, these were equal. See, the solution I am saying, case one without shunt reactor, I will say. case 1 without shunt reactor. I'll draw ABCD model of line. That it's one of the easiest way of analyzing. And it's a ABCD model of the transmission line wire. And this side we have a source, voltage source. This side we have a voltage source, and here we have some no load operation. Open circuit. No load operation means it's open circuit. So IR is equals to 0. And this is your sending end side, PS. And this point voltage is VR0. This point voltage is VR0. How is it VR0? No load operation. No load operation means how is it VR0? VR0 equals to VS by A. We studied in what we call ABCD parameters, VS by A, right? What is the parameter A? We have 0.9 at an angle 0 degree, 0.9 at an angle 0 degree. So it will come to be 1.111 times of VS. So there is a definite thing to say this VR0 is greater compared to VS in magnitude. So we have Ferranti effect. We have the Ferranti. So receiving end voltage magnitude under no load operation is greater compared to sending end voltage. Now simply in the very next slide, what I will do is same model I will repeat, but I will keep one shunt reactor at this place. Receiving end current is 0. Receiving end current is 0, but there we should make mod VR0, mod VS as equal. Mod VR0 and mod VS values as equal. Okay, I'm copying the same model. Same model I am copying here. So I'll say it is case 2. Okay, so I am adding this shunt reactor bank. Shunt reactor. How is the impedance of shunt reactor generally? How will be the impedance of shunt reactor? Plus J or minus J? Impedance of shunt reactor, is it plus J or minus J? Plus J symbol. So I can call it is JXR. Impedance of the shunt reactor is JXR plus J. All of you following this, please tell me. All of you following this one? Yeah. Please tell me, all of you following this? Nobody is responding. What happened? Okay, fine. Let's see this. After keeping the shunt reactor, this VR0 is equal to VS. VR0 magnitude. Moreover, magnitude of VR0 and magnitude of VS both are exactly equal. That's the thing. Now see this. So in the previous case, you are saying VR0 magnitude more than VS, but now you are saying VR0 equals to VS. How you say VR0 more than VS in the previous case mathematically? Mathematically, how you can say VR0 is greater compared to VS in the previous case? Anybody please tell me why? Why in the sense A is less than 1? Mathematically speaking, A value was less than 1. That's why we are getting VR0 more than VS. But how you can get this VR0 equals to VS means VR0 new also you can write if you want. So this magnitude of A, new value or equivalent value must be 1. Magnitude of A equivalent must be 1. If that's the case, VR0 magnitude new will be equals to sending end voltage magnitude. Okay, so simply you have to find out the overall ABCD of this one, and you pick up magnitude of A, make it equals to 1, get the value of XR from that. So equivalent ABCD, if you write A equivalent, B equivalent, C equivalent, and D equivalent will be equal to. So we have ABCD of line, multiplied with what are the ABCD of the shunt element? What are the ABCDs of the shunt element? 1, 0, 1 by Z 1. Yes or no? 1, 0, 1 by Z 1. These are the ABCD of the shunt impedance. Shunt impedance. Yeah. So now what you do is pick up only A equivalent from this one. Pick up only A equivalent. That will be sufficient. That will be sufficient. So it will be A into 1 plus B into 1 by JXR. B into 1 by JXR. A into 1 plus B into 1 by JXR. Let us substitute the values in this. A 0.9 at an angle 0. Observe 0.9 at an angle 0 is A. What type of line is this? What type of line is this? Anybody? Just by looking at ABCD, can anybody tell me what type of line is this? What type of line? I need a good answer from you. What type of line is this? Medium. Very simple answer. Long line, somebody is saying. Short line. Lossless line. Good. Transmission line is a lossless transmission line. For lossless line only, the angles will be like this. A and B angle will be 0. B and C angle will be 90 degree for the lossless line. Okay. Yeah, anyhow. B value 200 at an angle 90 degree. I will substitute here. By JXR means it will be XR at an angle 90 degrees. Let's simplify that A equivalent further. Simplify that A equivalent value further. So it is 0.9 plus 200 at an angle 90, XR at an angle 90. The resultant angle will be 0 only. So you get this like 200 by XR. You get it as 200 by XR. You take modulus of A equivalent now. Modulus of A equivalent. You don't have any angle, huh? You don't have any angle. So magnitude itself is this. You can see. Okay. So as we are saying, magnitude of A equivalent is equal to 1. So you write now 0.9 plus 200 by XR value is 1. Then the value of XR will come to be 2000 ohms. This is the shunt reactor reactance we have to keep at the receiving end side. Shunt reactor reactance we have to keep at the receiving end side. Okay. This 2000 ohm reactor is connected between what? Between what? Between A to neutral. Between A to neutral, we have to connect this one. Again, B to neutral 2000. C to neutral 2000 we have to connect. Following all of you means if you think about your receiving end side, this is A, B, and this is C. See, it's the receiving end side. At this place, we are connecting A to ground also. You can read if you want. We are keeping J 2000 ohm reactance or impedance, and B to ground also we are keeping J 2000 ohms, and C to ground also we can say J 2000 ohms. And one thing what you have to understood here is this is a star connected reactor bank. It's a star connected reactor bank. Right? Star connected reactor. Star connected reactor bank, should say. So let's take up some more problems with respect to shunt reactor bank. Next question I am going to take up. Yeah, see this one. In a 400 kV system, the Thevenin equivalent impedance with respect to a bus bar is 0.3 per unit on 400 MVA base. It is desired to keep a shunt reactor at that bus bar to reduce the voltage by 3 kV per phase. We have to reduce the voltage by how much number? 3 kV per phase. The three-phase rating of the shunt reactor in MVR will be how much? Three-phase rating of the shunt reactor in MVR will be how much? Simple question. See, in this question from data, anyway, I will be sending this question in the PDF file. No, just read the question. Read the question. 400 kV system. First statement is rated voltage is 400 kV. That's the meaning. Is it line to line or per phase? Is it line to line or per phase? Definitely line to line. 400 kV line to line. Okay. Thevenin equivalent impedance with respect to a bus is 0.3 per unit. Jet Thevenin 0.3 per unit on 400 MVA base. Jet Thevenin is 0.3 per unit. On 400 MVA base means S base. Three-phase value. 400 MVA. 400 MVA. Three-phase. Okay, next one. It is desired to keep shunt reactor at that bus bar to reduce the voltage by 3 kV per phase. Voltage reduction required. Voltage decrement required. Delta V. 3 kilovolts per phase. Okay, next. Rating of the shunt reactor is how much? Q reactor. What rating we should give here? Per phase or three phase? Three phase we have to give. In the answer we have to give three phase. Let's write per phase first. Let's write the per phase. What's the formula for this per phase? What is the formula for the per phase reactor rating? Anything mentioned regarding Thevenin voltage? Anything mentioned regarding three phase? Sorry, what we call Thevenin voltage. He didn't said anything about Thevenin voltage. As he didn't mention about Thevenin voltage, we will be going with an equation delta V into mod V by X Thevenin. What is delta V? 3 kilovolts per phase. Per phase. You write here phase. Better. Phase. It's also per phase anyhow. What is mod V per phase? You take 400 kV by root. Take 400 kV by root. X Thevenin given in per unit. X Thevenin. So Jet Thevenin 0.3. Of course, X Thevenin is also close to 0.3 only. You can take it 0.3, no issue. By neglecting that resistance value or by considering that X by R ratio very, very high. By assuming X by R is very high. X by R is very, very large. By taking that assumption, X Thevenin will be 0.3 only. That will substitute. But you have to keep that in ohms. You have to keep that X Thevenin in terms of ohms. Means that X Thevenin per unit we should multiply with what? Z base. You should multiply with Z base. Okay. So I'll write X Thevenin in terms of ohms. You attempt to get per unit value into Z base. What is that Z base? Z base will be V base line to line square by S base three phase. By that S base three phase. Okay. So X Thevenin per unit is 0.3. V base line to line square is 400 K whole square by S base three phase is 400 mega. So that kilo square and mega will be cancelled out. I think you may get this number 120. 120 volts. That you substitute in that, you will get the Q reactor per phase value. Multiply that with 3, you get three phase number. Yeah, let's see this. Q reactor per phase. Delta V, it is 3 kV. 3 kV. Okay. V phase 400 by root 3. 400 by root 3. By denominator 120. So kilo square na, it is mega. Reactive power means var. Mega var. You will get some value. You please tell me how much is that? And Q reactor three phase number we have to give in the blank na. Q reactor three phase. Anybody getting this per phase value? 5. 1 by 1 by √3. Check that. 0, 0 cancelled. The 4 and 10 by √3. I think it is 10 by √3 MVR. 10 by √3 MVR. So it is 3 into 10 by √3. 3 into 10 by √3. So it is 30 by √3. So it's √3 into 10. So it is 17.32 MVR. Without using calculator also you can do, I think. Without using calculator also you can do 17.3. So you have, do you have that option? Yes, option C is a correct. Correct option will be C. Correct option will be C. 17.32 MVR. Q reactor, 3-phase bill. Okay. Let's see one more question. One more thing. Let's regarding capacitor. Okay, it was regarding capacitor bank. It's regarding capacitor bank, but still it's okay. We will discuss that. We'll discuss that. See this question. So in a power system network at a bus bar, the voltage is 0.9 at an angle 0 degree. And Thevenin impedance with respect to the bus bar is J0.3. It is desired to keep a shunt capacitor bank. Now it is capacitor bank at that bus bar to raise the voltage magnitude by 0.1 per unit. Means earlier we have 0.9. Now we have to increase the magnitude by 0.1. So it will come to be 1 per unit. That's our target. 1 per unit you have to make. Okay. What is the MVR rating of the capacitor bank required in this case? S base 3 phase is 200 MVA. What is the MVAR rating of the capacitor bank required? Yeah. Kindly see this. Says one. See, it is some big network we have, and it is some bus bar. With respect to that bus bar, voltage is at 0.9 at an angle 0 without capacitor. So V Thevenin 0.9 at an angle 0. Thevenin impedance is at J0.3. Okay. Voltage rise required. Voltage rise required. Delta V how much? 0.1 per unit. Can we draw model? Thevenin model and proceed. Exact method can I follow? Can I follow with exact method? Can I follow with exact method? Yes. Yeah. So now in the earlier case, they have not given us Thevenin voltage. That's why we have used this formula and we got the answer. But now we can go with the exact method. Exact method means we should replace that whole network with the Thevenin voltage along with Thevenin impedance. What is the Thevenin voltage? 0.9 at an angle 0 degree, and this Thevenin impedance is J0. And this is a bus bar at which we are interested to keep capacitor bank. Okay, so I will add that capacitor bank with an impedance ZC, which is minus JX. Capacitor bank impedance is minus JX. Now, this is a capacitor voltage we have, VC. Capacitor voltage, VC. How much is that capacitor voltage we are saying? 0.9 is a initial voltage. After adding capacitor, we have to get a voltage by increase by 0.1 in magnitude form. So this is 1 per unit. That number will be 1 per unit. And the rating of the capacitor bank now, rating of the capacitor bank is nothing but VC square by XC. So it is 1 square by XC. So answer is 1 by XC. Answer will be 1 by XC. So we have to calculate the value of XC now. We have to calculate the value of XC. Simple, very simple. You find out this current how much? In the circuit, you try to find out that current. Try to find out that current. But you can say current I is equal to 0.9 at an angle 0 degree by it is J0.3 minus JXC is the current. J0.3 minus JXC. And if you do this, you get 0.9 at an angle 0. Okay, J is common. 0.3 minus XC you can get. That's the current. The current into ZC is a voltage VC. Na? VC is equals to I into ZC. So if you take magnitude of VC, it will be magnitude of the current into magnitude of ZC. Look at the thing, what I'm doing exactly. Magnitude of voltage VC, it's a magnitude of VC only. Magnitude of VC is 0.9 plus 0.1, that will be 1. That will be 1. Okay. Mod VC equal to mod I into ZC. Mod VC, 1 already we said. What's the magnitude of current? It is 0.9 by 0.3 minus XC, that J will be going out. If you take magnitude of the denominator, 0.3 minus XC only. And what is ZC? Magnitude will be XC again. Magnitude will be XC. Let's modify this one. 0.3 minus XC you send to other side. So you get 0.3 minus XC. And other one will be 0.9 times of XC. 0.9 times of XC. And you get 0.3 equals to 1.9 times of XC. So XC value will come like 0.3 by 1.9. Is it so? Kindly check. Committed any mistake anywhere? One, 0.9, this one, 0.9. Okay. Is it correct? Yeah, please kindly tell me, is it correct? How much is XC value? Anybody? How much is that XC? 0.3 by 1.9. 0.157. I don't think so. Just, let me cross check once again. VC equals to I into ZC. Current is that. Okay. J 0.3 minus XC. So mod VC is 1. So it is 0.3 minus XC. So XC value is coming very, very low. XC value is coming very, very low. It may cause 1 minute, wait for 1 minute. I'll tell you. XC number is coming very, very low, very, very low. Respect to this, if you take, respect to that, if you take, it will come. This VC may come less than 1, no? Less than 1, I think. Just check once. VC value may come less than 1 with those numbers. I'll tell you. Just listen here. See, XC value you got 0.157. That's okay. So if you substitute that 0.157 here, 0.157, and you try to divide this voltage between these two. Try to divide the 0.9 per unit between these two. Then how much you are going to get at this place? That you please cross check. Please cross check. That will be roughly 0.9 into it's minus J 0.157 by J 0.3 minus J 0.157. How much is this number? Anybody please tell me? What is that number? It's not, it's a wrong answer, Ramakrishna. Just kindly follow it. 0.9 minus 1 by total reactance. Please tell me this number. 0.9 into minus J 0.157 is the capacitor impedance you got recently, right? So that by overall impedance. What is this value of voltage you are getting? What is this value? Are you getting 1? Exactly. It may be 1. It may be 1. It is going on the higher end. 0.988. 0.988. But we need that voltage as 1, right? We need that voltage as 1. That's the issue here. Okay, I'll tell you. Just listen. So what you do is, this current we have, this current. You take minus J common, then you will be getting this like Xc minus 0.3 unit. Okay, now you take magnitudes and all. Now you will be taking the magnitudes and all. So in the denominator here, you will get Xc minus 0.3. Xc minus 0.3 you take. And then if you move ahead, it will be Xc minus 0.3, Xc minus 0.3, and then you take that 0.9 to this side, 0.3 to the other side. Okay, so you will be getting Xc is equal to, sorry, you take this to this side, 0.1 Xc will be equals to 0.3, and Xc will come to be 3 per unit. Xc will come to be 3 per unit. This is the correct one. That number is perfect. 3 per unit. Xc value 3 per unit. That one 0.9 Xc only, na? 0.9 Xc. Multiplication of these 0.9 Xc. Right. Now, the rating of that shunt capacitor bank is 1 by Xc. So it will be 1 by 3 per unit. 1 by 3 per unit. But that also you can say if you want, Vishnu. That also you can say. You can do it by using voltage division principle. Yes. Okay. Please check this one. This is in per unit, but you have to get this number in MVA. So we have to multiply with base. That base is 200. So Q shunt capacitor absolute value in MVA. Q shunt capacitor absolute value in MVA will be equals to Q shunt capacitor per unit number multiplied with S base 3 phase. So Q shunt capacitor per unit is 1 by 3 and S base 3 phase how much? 200. So it's 200 by 3. MVAR come to be MVAR. I think it is 66.67 MVAR. 66.67 MVAR. Yeah. Done? So next, see this one. So it's a previous GATE examination question. Previous GATE exam question. Go through it quickly. See, a shunt reactor of 100 MVAR is operated at an increased voltage by 10% of its rated value, right? And reduced frequency by 10% of its rated value. The reactive power absorbed by the reactor is dash approximately. See, first of all, whatever the 100 MVAR he said here, 100 MVAR, that is the amount of reactive power absorbed by reactor with rated voltage and rated frequencies. Rated voltage and rated frequencies. Okay. If the operating voltage and frequencies are different than the rated values, definitely reactive power absorption is going to be changed. Okay. Yeah. So let's say, first of all, if I have one shunt reactor simply like this, operating at some voltage V with a reactor reactance of XR. What is that Q reactor absorption formula? Q reactor absorption formula will be V square. I'll write V simply, but there is a magnitude of voltage. V square by XR, na? V square by XR. That is nothing but V square by XR is nothing but 2 pi F into inductance. 2 pi F into inductance. Inductance is anyhow constant. So you can call now Q reactor will be proportional to voltage square by frequency. Q reactor is proportional to voltage square by frequency. Voltage square by frequency. This is with respect to reactor. For example, if you have a capacitor, if you have one capacitor here of reactance value Xc, voltage is V. What is Q shunt capacitor? Proportional to, equal to voltage square by Xc. Voltage square by capacitor reactance. Else you can call it as V square into 2 pi F into capacitance. 2 pi F into capacitance. Where you can call this Q shunt capacitor will be proportional to voltage square into frequency. Q shunt capacitor proportional to voltage square into frequency. These two equations will be simple. Whenever we have a change in the operating voltage and frequency, accordingly, the reactive power absorption or delivery by these elements are going to be changed. Based on these equations also, there is a possibility of getting questions in the exam. Okay. Yeah. So let's see. The problem, what is it? Problem. 100 MVAR. I'll say it's a Q reactor 1. It is 100 MVAR. At how much voltage and frequency is rated values. Rated values means you call it is simply V1 F1. V1 F1. That's it. What is Q reactor 2 value? Is asking how much is a Q reactor value at how much voltage? How much voltage? Increased voltage by 10%. So 1.1 times of V1 voltage, reduced frequency means 0.9 times of F. And you know, just now we said Q reactor is proportional to voltage square by frequency. So you can say Q reactor 2 by Q reactor 1. Q reactor 2 by Q reactor 1 is 1.1 V1 square by 0.9 times of F1 by denominator V1 square by F. Do the calculations and you will get this Q reactor 2 is equal to Q reactor 1 100 multiplied to 1.1 square by 0.9. Yeah. 1.1 square by 0.9. How much is this? How much is this one? 134.4. 134.4 MVAR. 134.4 MVAR. That is the amount of reactive power absorbed by reactor with a change in the operating voltage and frequencies. Yeah, so this is about the shunt elements. So in the tomorrow class, tomorrow also we have a session from 6:30 to 9:30. Tomorrow class, we will be taking up the series capacitor and remaining synchronous motor applications. Okay. So if you have any doubts, you can ask me. So if you don't have doubt, you can leave. That's your wish. If you have any doubt, please raise your hands now. Please raise your hands. Vijay.
Hello, sir.
Tell me, Vijay.
Sir, page number 34 है.
Yeah.
Sir, it was asked in the question that per phase capacitance.
Per
Our we
phase
have-
means delta connected capacitors per phase. That's the meaning.
Okay. If it is not given anything like it is delta connected or star connected,
Then we
have
can't
to
do.
go for-
There is a insufficient data in the question. They should give. They should tell whether the capacitor bank is in star or delta.
Okay.
Okay.
If nothing given, what should we answer?
Nothing given, you go with star only.
Oh, okay, sir. Thank you.
Okay. Okay. Yeah, thank you. Thank you all. Thank you. Salman Khan, Shreyas, Shilpa. Anil Kumar. Anil Kumar.
So good afternoon, sir.
Tell me, Anil Kumar.
Sir, in 17F, sir.
17. Okay, tell me.
Sir, could you explain this again, sir? I did not get.
See, actually, under-excited machine is going to act as sink of Q.
Sink of, yes, sir. Okay, sir.
Over-excited machine will act as source of Q.
Okay, sir.
Q means which Q is that? Leading Q or lagging Q?
Sir, sink of Q means which is observing the reactive power.
Very simple. Sink of Q, source of Q. Q means which Q? Lagging or leading?
Sir, lagging.
Both are lagging.
Yes, sir, both are lagging.
Okay. So now you check which machines are under-excited. Tell me which machines are under-excited?
Sir, induction generator, synchronous generator, synchronous motors, induction motor.
Read carefully. Ramakrishna, read. First one, is it under-excited or over-excited?
Sir, under-excited, induction generator.
Anil. Second one?
Sir, that also under-excited, sir.
Third one?
That also under-excited, sir.
Fourth one?
So over-excited.
Fifth one?
Under-excited, sir.
So 1, 2, 3, 5, these are under-excited machines.
Okay, sir.
Sink of which Q?
Sir, sink of.
These are sink of Q, na?
Yes, sir, sink of Q.
Sink of which Q?
So, that point only I did not get, sir.
Already you said the answer. Under-excited machine is going to act as sink of Q. Yes or no?
Yes, sir.
Sink of which Q?
Sir, lagging.
Lagging Q. 1, 2, 3, 5 are under-excited machines.
Yes, sir.
Under-excited machines means what?
This observing reactive power, sir.
Absorbing reactive power. Which reactive power? Lagging or leading?
Lagging, sir.
Means delivering leading reactive power only, na?
Yes, sir. Delivering leading reactive.
That's it.
Okay, sir. Thank you, sir.
Understood, Anil?
Yes, sir. Understood, sir.
Yeah. Kumar.
Sir, good afternoon, sir.
Good afternoon. Tell me, Kumar.
Sir, last second, sir. From last second, sir.
You tell me what's the slide number?
Slide number I did not remember. React, not this one. Next one.
This one?
Yes, sir. So here VC is equal to you take mod I into mod ZC. If we take it like in VC is equal to I into ZC calculations, it will give some other answer.
No, it won't give some other answer. It will be giving same, no? I you substitute here.
Yeah.
ZC also is substitute here.
ZC we have to substitute minus JXC, right?
Minus JXC.
Because of that minus 0.9. So
You are taking magnitude, no? Ultimately, after that one, you are taking magnitude.
if we take with the magnitude and angles, the resultant is same.
Kindly look here. I into ZC, okay?
Yeah.
I you are substituting this one 0.9 by 0.9 by J 0.3 minus XC. It is I.
Yes, sir.
What
into
is
minus jxc.
minus jxc? Minus j will be cancelled out. It
Minus
will be minus 0.9 xc by 0.3 minus xc.
Yes, sir. Here one.
This is I into zc.
There is v one.
This is vc.
VC.
What is modulus of vc? So it is modulus of I into zc.
Okay.
And you take modulus of numerator and modulus of denominator. What's the modulus of numerator? 0.9 into xc. Denominator magnitude 0.3 minus xc. This is one option. The other option will be that mod vc will be equal to if you take that minus sign to the denominator and numerator will be 0.9 into xc only, denominator will turn to the xc minus 0.3. Two options here. Getting understanding what I am saying to you?
Yes.
Among these two options, whichever option suits, we have to take that one. This one will be suitable. Why it is so means in this case xc number is coming very, very low, which may not be practical thing to happen. xc number will be in the order of thousands of ohms practically.
Okay.
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 Any other doubt you have, Kumar?
No, sir. No.
Yeah. Ramakrishna.
Yeah, hello. Good afternoon, sir.
Good afternoon. Tell me.
Sir, here no need to take off magnitude, no, sir. Directly we can substitute one angle 0 and we can find, no, sir. Why to take magnitude again?
If resistance is given.
Okay. Then we should take here, but here we are getting directly without magnitude the required answer, sir.
Here we are getting that's okay, Ramakrishna.
Yes, okay.
I also know it.
If resistance
If the whole network is reactive in nature, you don't get a phase angle change from one point to other point.
Yes, sir. Yes.
Network is pure reactive. But for example, in the Thevenin impedance, if there is some resistance,
then we have to take it. Yes.
this is only the procedure. There is no other way of doing it.
Okay.
That's why I said here it is VC. Magnitude is 1.
Yes, sir. Magnitude 1.
Magnitude is 1. I don't know angle.
Okay.
That's a problem. Okay.
Yes, sir.
But having an idea like this, okay, that whole network is reactive, so I will be getting angle at 0 degree only. Then you can take 180 angle 0 degree and you can continue.
Okay.
You can do it. Yes.
Once 14F, sir.
14.
14F, yes, sir. 1.
Okay, tell me.
This before the inductor or this.
Okay.
Sir, here how this minus I angle is taken. Generally, this P equal to VI of cos theta means theta will be angle between V and I or I and V.
P and I. I and V or V and I angle will be same, no?
Oh, no. Yes, but if we take VI of sin theta, we will get
that depends upon that VI conjugate and V conjugate I again.
Okay.
What equation you are using? Is it VI conjugate or V conjugate into I?
Okay. So what is generally under excitation means?
Low field current.
Generally, we should where inductor load is there that we should take as under excitation or how?
No. You ask me with a specific device first to tell me for what device you want me to tell.
So you have given example for synchronous generator under excitation. So how that?
Okay. See, synchronous generator is under excited means field current is less.
Okay, sir.
Field current is less means induced EMF is less in the machine.
Yes, sir.
If the induced EMF is less, it may be less than the terminal voltage.
Okay, sir. Yes, sir.
Then the reactive power will flow from.
Yes, sir. Reverse. Okay.
Terminal to generator.
Terminal to yes.
So it is absorbing the reactive power.
Yes, sir. Leading power factor will be leading.
Power factor leading that and all okay. First you tell about Q direction. Who will decide power factor? Is it leading or lagging? Current delivered by generator will decide.
Current.
Current power factor definition is what? Cosine of angle between voltage and current.
Current, yes.
Once if you are saying current, you should stick on to current. That's it. If it is a generator, current delivered, you have to consider. If it is a load, you should consider current taken.
Taken.
Yeah.
Yes, okay, that's it.
Okay.
Thank you. Sir, happy.
Thank you, Ramakrishna. Thank you. Pratyush,
Hello, sir.
tell me, Pratyush.
Sir, I have a statement regarding shunt capacitor, sir. Is it right or not? Can you please say it?
Tell me.
Sir, a industry is operating with a certain group of induction motors, sir, at a poor lagging power factor, sir.
Okay.
And at a distance of 10 to 20 kilometers, household load is present, sir.
Okay.
So that due to that poor lagging, the voltage at the household load is less than rated, sir.
Yes, correct.
Sir, by connecting a shunt capacitor bank at industry, the overall system power factor is going to be increased, no, sir?
Not that household load.
Yes, sir. But the voltage at the household load will going to increase, no, sir?
Increase, definitely. Yes.
Sir, that means the machines operating in the industry for the mission power factor is not going to increase, but the overall system power factor will be increased,
Overall factory power factor will increase.
but not the individual machine, no, sir?
Not individual machine.
ఓకే సార్ దట్స్ వై టు అంటే ఇప్పుడు హౌస్ హోల్డ్ దగ్గర వోల్టేజ్ డిక్రీజ్ అవ్వకుండా ఉండడానికి కోసం ఒకవేళ ఇండస్ట్రీస్ దగ్గర ఉంటే ఇండస్ట్రీకి పవర్ ఫ్యాక్టర్ కెపాసిటర్ బ్యాంక్స్ పెట్టుకోమని చెప్తారు కదా సార్?
No. Actually, those industrial people not only charge for kilowatt consumption, they will be charged even for kVA and kVR consumption.
Yes, sir.
So to reduce their electricity bill, they have to go for capacitor bank installation.
Okay, sir.
That is their own requirement. Unless
Okay,
otherwise, the distribution company can't command them. You have to put a capacitor bank. Your voltage is falling down. That the distribution company will not tell as a word.
Yes, sir.
They will tell this one by a charge.
Okay, sir.
Electricity charge they will implicate on them. So those people are forceful to keep a capacitor bank. They
Yes,
don't have
sir.
other choice
Yes, sir. Yes, sir.
to reduce the power bill.
Okay, sir.
Generally,
Sir.
generally the distribution company should not keep a fine on some people who are maintaining low power factor.
Yes, sir.
Right? They have to put that in the electricity charge so that they will implement their requirement.
Okay, sir.
Yeah.
Sir, sir 45F, sir.
Okay, tell me.
Sir, that ABCD problem, sir. Before, sir, in this problem, sir, if the voltage of the that long transmission line is given, can we go by this formula, sir? Q shunt capacitor is equal to delta V into mod V by X.
If ABCD are given, ABCD calculation method is exact.
Yes,
This
sir.
is exact reactance you got.
Yes, sir.
But the Q shunt reactor equals to delta V mod V by X7, that's approximate.
Yeah, okay, sir.
There you neglected delta and all.
Yes, sir. Yes.
Wow, what you take V? What you take delta V?
Sir, if the voltage is given, sir, I am saying.
Even though voltages are given, if the ABCD parameters are mentioned in the data, you have to go with the ABCD only.
Okay, sir.
Pratyush,
Yes, sir.
if they have given a clear idea in the problem, we have to go or you have to follow exact method only. We should not go for approximate. If the
Okay.
data insufficiency is there, then you can go for approximate calculations.
Okay, sir.
Okay?
Okay, sir. Yes,
Yeah.
sir. Thank you, sir.
Vishnu,
Good afternoon, sir.
tell me.
Sir, it is regarding this AC steady state analysis.
Okay, tell me.
Sir, in AC steady state analysis, even in the transient condition as well as steady state, we'll have a proper, we have reflection.
Yes, correct.
So in same as what we analyzed in DC, for positive half will be same as that of DC.
Okay.
And for negative half, then how would it happen, sir? In case of transient case, I'm asking in AC.
Negative case means?
Negative half of the, you can't be, so on an app, you can't say based on the average voltage anyway. So only you can describe AC transient phenomenon based on instantaneous values, no, sir?
Instantaneous values. That's okay. What's your doubt in that now?
My doubt is in negative half of the instant. Negative voltage.
Then instant is also negative only, na?
So the entire phenomenon will be reversed.
Reversed, obviously, yes.
And in the steady state also, wow, I didn't get in the case of steady state, sir. In steady state also, how is it happening, sir?
So see, actually, in case of DC, your voltage will be constant with respect to time.
Yes, sir.
But again, here voltage is continuously changing with respect to time, right? If the voltage is continuously changing with respect to time, and if you have a mismatch between ZL and ZC,
Yes, sir.
definitely you get the reflections continuously.
Oh,
In case of DC, why it is settled down?
because the magnitude remains
Constant.
constant after some time.
Constant. But here it is continuously varying, na?
Here, even in the transient case also, the magnitude is
Same
varying
thing
with
will
respect to
happen, same
time.
thing.
And in
Yes.
steady state also it is varying.
Yes.
Okay, so that's why it is moving forward and backward.
Yeah.
Okay, so
Okay.
that's, yes, sir, that's one. And then, sir, this regarding while you explain this tabular column in the synchronous machine, under this underexcited for sync of Q, this you mentioned it as it delivers leading current to the and power factors leading.
Yes, correct.
And that time you also mentioned that it is same as something like capacitor bank. That part, and it's same as
I
something
didn't
like
say capacitor bank.
I mean, it's same as something like something based on capacitor. Also, you mentioned at that point.
No. See, actually, while you are defining power factor of the generator, you should think about what's the nature of load.
Okay, sir.
Load will decide what nature of current should be delivered by the generator.
Yes, sir.
Ultimately, load is the thing which is deciding the power factor of generator also, right?
Yes, sir.
Okay. If you keep the load as an inductive load is taking lagging current. So generator should supply lagging current. So generator power factor is lagging.
Okay, sir.
If you keep your load as capacity load takes the leading current. Generator should supply leading current. So generator power factor is leading.
Okay, sir.
That's it.
Okay, that's done. And sir, and in this thing, same like previous somebody asked, this induction machine connected induction motors running in parallel supplying a household. Like he said, sir, we are connecting a voltage compensation, sir. And let's say for increasing after connecting the compensation for very short, like for short time, then I'm increasing the power supply into the induction machine.
Okay.
So will the voltage increase?
After adding capacitor bank, you are saying?
I mean, in order to increase the voltage after adding capacitor bank, then what I'm saying is I'm again increasing the power also.
Which power? Real or reactive?
Real, sir.
If you are increasing real power, again the power factor might be affected, right? Based on that.
Then voltage also will increase at the bus.
Change. I don't say increase or decrease, it will change.
Then we can just remove the capacitor bank if it is the operating voltage.
No, you are saying that real power is getting increased.
Yes, sir.
You are adding extra real power demand.
Yes, sir.
See, very simple logic. Whenever you are adding extra real power demand, current flow in the system is more.
Yes, sir.
Voltage drop is more, and your resultant voltage is less only, na?
Still, you will need bank. Okay, sir. All right, sir. That's it, sir.
Yeah. Pratyusha.
Sir.
Tell me, Pratyusha.
Sir, in one sum we calculated V5, V7, sir.
Yes.
In that among V5, V6, V7, which one is reflecting and which one is instant? Once explain it, sir. I didn't get that.
No, first V1 is injected, that is incident.
Yes, sir. V1 to V4, I have clarity, sir.
V1, V2, V3, V4. What is V5? Reflection into the cable, right?
Yes, sir.
Right? Reflection into the cable.
Yes,
that will act as an incident to the next junction.
Okay, sir. Whatever
Okay?
V6.
Whenever V5 is incident, V6 is refraction to the line A.
Yes, sir.
V7 is the reflection from the junction, but that is flowing into the cable only.
Okay, sir.
So that will be a refraction into the cable also we can consider. But with respect to V5, if you talk, with respect to V5, V6 is refraction, V7 is reflection.
Yes, sir.
With respect to cable, if you talk, V7 is a refraction.
Okay, sir. Got it, sir. Another doubt, sir.
Tell me.
In one tabular form, in that induction motor, why it is under the sync of Q, why it is lagging power factor, sir?
What is induction motor power factor? Lagging only, na? The absorbing
Ah.
reactive power, right?
Yes, sir.
Acting as an inductive load. That's it.
Okay, sir.
Okay.
And in 13th slide, sir.
13.
Yes, sir.
Tell me.
In that second case, how we got that 180 and angle 180, sir?
I have
Whereas
written
in
here. Minus 1 will be written as 180 angle 180 or 180 angle minus 180. Anything. Minus 1.
That also. In shunt capacitor bank, case 2 once open. Sir.
Tell me.
In the diagram, you have mentioned Q load minus Q shunt capacitor. How you write
Apply
this?
KCL here. Apply KCL. This is absorbing Q load. This is injecting Q shunt capacitor. How much should come from the line?
Sir,
Okay.
Q load plus Q shunt capacitor.
This is Q shunt capacitor injection. Q load which is taking up. You take this is some QX. QX plus Q shunt capacitor equals to Q load, na?
Sir, my network is getting this.
You assume this line injection as QX.
Okay, sir.
QX is injection. Q shunt capacitor also injection.
Okay, sir.
That is equals to Q load, na?
Yes, sir.
Then what is QX? Q load minus Q shunt capacitor.
Okay, sir.
Okay.
And then one sum, sir. Delta factor capacitor bank. In that you said that overall power factor is 0.8 lakhs.
Okay.
So to maintain that 0.8 lakh, are we keeping that induction motor power factor as 0.6 lakhs?
We are not keeping it. It is operating at 0.6.
Okay, sir.
Okay. It is operating at 0.6 and we are keeping capacitor bank to make the overall to 0.8.
Okay, sir. Thank you.
Understanding? Okay.
Yes, sir.
Gopi Raju.
Hello, sir.
Tell me Gopi Raju.
One student asked about industrial loads just now.
Okay.
If you can increase industrial load and maintain a low power factor, this companies
I am unable to listen you clearly. Siva?
How, sir?
Okay. Tell me.
Just now one student asked about the industrial load.
Okay. Yes.
If you keep on the industrial load maintain a low power factor, reactive power demand by the industrial load.
Okay. What's your doubt?
Discom companies will impose more electricity bill use.
Yes.
My question is, irrespective of the reactive power drawn by the industrial load, energy meters will measure only real power, no?
Who said?
Electrical measurements.
No. Okay, electrical measurements. You studied about energy measurement. Have you not studied reactive power measurement there?
Yes, sir.
Have you studied or not?
Okay.
Present day meters are measuring both real, reactive, both. There is a meter like tri-vector meter something.
Okay.
It will measure both they will measure.
Okay.
Even you see your household meter, there it will display the power factor also.
Okay.
By using the power factor and real power, we can measure reactive power, right?
Old meters, number of revolutions.
Old meter, see that that rotating meter may not give. Digital meters will give. Okay. Even by rotating meters also, they are capable to measure the reactive. But we need a separate element for it.
Okay.
So 2 elements I should give, one for real power, one for reactive power. But here in digital meter, only one meter itself is capable to measure all. Voltage, current, power factor, real, reactive power, apparent power, all the things.
That means in older days, the discoms will lose income, sir.
Yeah, now
Yes.
that's why they are replacing all old meters with new meters. No, now you don't find any running meters today. It will be digital meters only now.
Like that.
Okay.
Okay.
Yeah. Naveen Sai.
Sir, good afternoon, sir.
Tell me.
In shunt reactor, sir.
Hmm.
After adding shunt reactor, the power factor is increasing, sir.
If the load is leading.
Okay, even though if there is a light, we are connecting at a lightly loaded condition, sir.
Lightly loaded condition means which system is that? That and all depends, Naveen.
My general, I mean,
If it is of EHV line and UHV line, that's a different story of lightly loaded condition.
Okay.
Generally, we
My
connect the
doubt
shunt
is this
reactors
one,
only in
sir.
the EHV and UHV lines, not in the 130 kV line, 33 kV, 66 kV. Na?
Okay, sir. That means we should not decide like this. Even though we are connecting shunt reactor, the power factor may increase or not, but the voltage is coming down.
Coming down, yes.
Yes. Okay, sir. That's. I mean, my doubt because generally when we connect inductor, power factor will be reduced, no, sir. Generally.
Yeah.
But here it is increasing. That's why
No,
confusion.
if the initial load itself is leading in nature, then it will increase, right?
Okay, sir.
Okay.
Thank you, sir.
Akshay.
Hello, sir.
Yeah, tell me, Akshay.
Sir, we did one problem like the dead end tower and substation problem with cable.
Yeah.
Sir, in that problem, like case when you mentioned that like if the 100 kV voltage is traveling, then 2 times that voltage 200 kV will appear at the substation, right?
Yes.
And then that voltage would change the voltage of the transmission line.
Yes.
Yeah. So like in the second case also we are getting some 36
36.36.
Yeah, that
36.36 will come back.
Okay, sir. So like, what is the difference? Like, I didn't get there. Like,
No, that rate of rise will be less. No, all of a sudden 200 kV is appearing on the overhead line.
Okay. Yeah.
In the first case.
Yes, sir.
But in second case, you see 36.36 kV coming back, and there you get a reflection and refraction between cable and overhead line.
Yeah, cable and overhead.
But initially, what is the voltage experienced by line? Initially 100, then it was reduced to 18.18.
Oh, okay. Yes, sir.
That's the meaning of reduction. Okay.
Okay, sir. Got it. Thank you, sir.
So any more doubts? We close the session. Thank you.